Oh, yeah. Do you happen to know where I should upload the file?
Yes.
I couldn't find the
So I know there's the link went out in
Slack or
in email. I think it should have been in both. I'm not in the fellow Slack, so I don't know.
Okay, but
if it went out. But
we received some email. I checked, but yeah, I couldn't find the email, so yeah, I might be messing up something. But yeah, that's what's the title?
yeah, let me.
Yeah, thanks.
So I'm not 100% sure about the close side.
Symposium, yeah. I only received Symposium draft program, so
There is the. Right. Yes, that would be fine.
do you know
Yeah.
when we received the email about the old instruction to upload the file? What kind of time? Yeah, I couldn't find the email.
I don't know what day it was, but maybe if you search by like the NHFP email address.
It's
NHFP at it might be STSCM.
STS.
It is.
Yeah. Oh,
I want to say it was maybe like within the last 7 to 10 days.
okay. Yeah, I couldn't. I'm afraid
This is the link.
Okay, so
Caltech.
okay, maybe let me directly type the yeah. Caltech or
Yeah, we can bring up yours so we can check it.
I have issues uploading it. I didn't change it.
Dot key. What is this?
Has nobody else used Keynote?
No one has used Keynote, so I'm glad you came. Okay.
Just trying to-
Blue is the
Yes.
Yeah.
It's
Good.
Nice. Okay.
There's one down.
That's the big one, right?
yeah.
Yeah, they're actually not, the file sizes are actually not that big, but
Oh, no,
it's gonna
not
get-
file size.
Yeah.
This is the important thing to check. Yeah, of course. I'm glad it worked.
Yeah, it seems that I found the email, but I'm still missing the this is the program.
Yeah.
Program. Science session will be
There we go. Submission page. There it is. Okay.
And there's any format for the file name? Okay, got it. Okay, thank you.
Yeah.
Sorry for that.
No, I'm glad we can get you before it's time to talk.
Each of them is
Okay.
So optical. Yeah. And these are the and later. Stat.
Thank you so much for running and keeping all the talks going so smoothly.
Oh, yeah, sure, no problem. Don't take me yet because I haven't had a chance to catastrophically tear everything apart yet.
Well, no matter what you do, it'll be better than one of the first double S's that I went to.
Yeah.
We ran out of electrical power, and so everyone was literally like making sine waves with their hands, and, gestures and things like that.
Interpretive dance.
Yeah, I really want to see your interpretive dance.
Well, we run out of power.
Let's take a look.
And I hope.
Got it.
I'm gonna go
Seiji. Got you here.
My talk will be 4 p.m. So yeah, I hope.
Yeah, I mean that's enough time. So is this downloading? This is on Keynote 2. This is it. Got it.
Thank you.
Okay, sweet. All right, and we are set for the rest of the day. Boom.
This is probably get better. This is like another problem. This is first. This is just like, I think it's also most right. Actually, no, I'm not sure. Is this the green? Yeah, should be. So because
No, yeah. Since this extraction, we've got but we can probably go back and basically we're specifying and then I expect that we will get approved data on that by 2 months. So that this speculative very close. Right. If this is all real, there's a lot you can do in there because there's, yeah, everything like university. Yeah, we should. Basically. This is that aspect. So supernova should be a self trace, and so you can have sort of where the house back like these partials. When you got your head out yeah. Victoria's first, right? Tomorrow morning. Yeah. So she came and asked me, so, and then the moment I just set up my specs, and I said, probably not. But if it's easier, we could share, we could just have this slide. We could do that, yeah. Or just plug your laptop. I've already well, because our laptop is running this. Yeah, as well as. We should have a couple of slides. Yeah, as long as they're not. One other mission, those slides are called where she actually so if she secrets it out, that's that page, that's no one else can get her. So this is. That's correct. Yeah. So yeah, or she could just put it directly on that computer too. Yeah, if you want like. Straight to someone here, that'd be fine. Yeah, flash drive or something, but I don't know if it's just one, we'll like one slide set or just we'll shut down YouTube. Oh, yeah, right. She did, yes, we asked us to do that, and she asked us not to. So I know that the grants, people don't have anyone, they're just gonna answer the question. It might be, and the faculty, it's just a panel. No, that's what well, we should double check to see. I think the panels are. No, they are, but I don't know if any of them have any slides they want to show. And we'll check that. This is the sorry, Victoria. Yeah. She so if we want to just do it, it's like we just have to yeah. If that's your easiest way. Sure. Actually, right on the side, I'll ask. Yeah, I was there. Yeah. Oh, yeah. It's like there are actually busy things that it's like you find a better way. Yeah, I just like
Oh, yeah.
Oh. Yeah, so I was like, there's one person. Yeah, no, because they want, because they're one. Yeah. Yeah, yeah, I want to think about it. Spaced out.
It's a shame. I like to, since I make a point.
Yeah, that's the only thing I feel like the little bit of everything that we go participants can see where you're pointing to. It's not very good.
That makes
Drop
sense.
drop this, you got it.
Speaking. Second, is this already turned on?
It is. Wait for your chair.
I'll be the chair. If you want to be more, yeah, but I will share. 2 minutes for last minute, right? Okay, so I'll give you a markup 10, you speak up.
Yeah, we've got this thing yeah.
Okay, I think for the online people. Hi, we are back. I hope you had a nice lunch. We are getting started with Gord Howard. He's gonna tell us about endorse, why all this stellar activity is so frightening or not. And yeah, let's take it away.
I'm excited to be back with you all this year, and I'm also very excited to be the first talk after lunch rather than a talk right before lunch. So with that, I'll go ahead and take it away. TESS has now measured the optical flare rate of essentially every bright nearby star in the sky, with over 1 million flares from over 140,000 stars in the primary mission alone, as you can see in this color magnitude diagram from Feinstein et al. 2022, which shows the flare rate as a color bar with darker colors representing higher flare rates. By the end of the second extended mission, which is coming up soon, TESS will have observed more than 3.5 million flares at cadences from 20 to 200 seconds in the full frame image mode. And of course, wide field, high cadence time domain surveys, such as NGPS, FASN, Everyscope, and others have also observed thousands of flares in other bands, some of them even simultaneously with TESS. However, only a few dozen flares have simultaneous UV and TESS observations. At these wavelengths, the sky is dark. So these are all of the simultaneous observations that we have, where we have TESS on the x-axis and some UV observations that are fully simultaneous and high cadence on the y-axis. There aren't a lot, and only 17 of these have 20-second cadence observations covering the peaks in both wavelengths, making it very difficult to assess what the true distribution is. And as you can see, this also leads to a large amount of scatter in these relationships. In the absence of more simultaneous data, the standard approach is to say, well, we know that optical flare spectra are often consistent with a 9,000 Kelvin blackbody. We'll just extrapolate that into the UV and call it good. The problem is that doesn't work. So here's a 9,000 Kelvin blackbody overlaid on this plot with 12,000 Kelvin, 16,000 Kelvin, and 26,000 Kelvin blackbody. And you can see an order of magnitude scatter in the actual amount of UV energy coming from the optical, sometimes above and sometimes even below the 9,000 Kelvin prediction. And so we know not just from these few simultaneous flares, but also from time averaged observations with TESS, Galitz, and Kepler, that there's a lot of work to be done in optical to UV scaling relationships. Why does this matter? It matters because only the near UV contribution and the FUV contribution of these TESS band optical flares drive photochemistry in exoplanet atmospheres. And so if you want to use TESS for understanding the stellar inputs of your exoplanets, the pathway, again, to understanding planets is going to lie through their stellar flares. And so here you can see two different synthetic flares that I've injected into a spectrum from Epsilon Eridani, and they both have the exact same energy when observed in the TESS bandpass, yet they differ by about an order of magnitude when you get out into the FUV, and even close to an order of magnitude in the near UV, leading to very different conditions for photochemistry. As a result of lack of multi-wavelength observations means we do not know what impact optical flaring has on exoplanet atmospheres without being able to constrain the two bands to better than 100% error. So in the meantime, given the state of the field, is there anything that we can learn from 20-second cadence observations to help us improve these TESS to near UV relationships that we couldn't have learned in the 2-minute cadence data? And then, going forward from that, what can we do to actually improve the numbers of simultaneous flares going forward? So we look at a large sample of simultaneous flare observations in the near UV with SWIFT and in the optical with TESS. And then I just want to come back to this plot really quick and remind you of this order of magnitude scatter. We want to know, can we use what's happening in the peak of those simultaneous observations at the high cadence to predict or lessen that scatter in some way? And so the thinking behind this is when we convolve near spec observations of flares with the TESS bandpass, you get a TESS light curve like what you see on the bottom, and you see a continuum evolution like this on the top. And we find that the effective temperatures of the flares are actually more comparable to what you would expect in the near UV in these times than during the decay. So there's this idea, instead of just integrating the entire flare energy in the optical, why not limit the optical energy to just the full width at half maximum to try to reduce some of the uncertainty due to these cooler temperatures during the decay? And so we try that. We try predicting the flare energies using just the full width at half maxima and the resolved observations, and then also using the entire energy of the optical flare, and we're able to reproduce the true UV energy with about a 50% improvement. So we're making some progress. We also find that a lot of these flares have time lags, and there are connections between the shape of the light curves. And so we see time lags of about half a minute up to about 5 minutes on our sample. And we also see that the shapes of the light curves in the UV and the TESS band are connected. And namely, the time integral of the near UV light curve is very proportional to the shape of the TESS band light curve. And so when you have simultaneous flare observations, you can use what you're observing in one band to infer what the shape of the light curve would be in the other band. And this is really helpful in terms of thinking about planet injection recovery around active stars. There's a lot going on in this plot, so I'll take a minute and walk you through it. The top band are simultaneous swift near UV observations, with gray points being synthetic data that I filled in where TESS was observing a flare, but Swift was behind the planet. The middle panel is the simultaneous TESS data, and you'll notice a blue trend that I fitted to the top line. That blue line is the Tovav Mendoza flare template that I fit to the UV flares. The orange line in the next panel down is where I've taken the time integral and left with the only free parameter, the amplitude of the flare, not the shape of the flare. And so that way it helps to reduce over or under fitting. So we can then fit with that constraint and then remove that fit to produce the TESS band residual. I'll also point out that these observations, even though they are fully simultaneous, have been stitched together in time where they were actually taken when at different times because, again, of the Swift duty cycle going behind the Earth. And so we need to stitch them together, again, for the purpose of injection and recovery tests. So we do that. And we have this question, can we improve our planet detection capabilities when we have simultaneous UV data? So we both inject planets without detrending, which is shown in magenta, and with detrending, which is shown in cyan, and we find that we are in fact able to recover smaller planets. And in this particular case, we are using the example of a K7 dwarf, which is fairly bright even for distant young active stars, and we're able to move all the way from a sub-Neptune into even a super-Earth regime when we inject across orbital periods of about a half a TESS sector and transit depths consistent with the values I've shown here. Going back really quickly, this is the wrong way. Going back really quickly, the reason this is important is if you see these two back-to-back flares in the TESS light curve, that's a common false positive scenario or even a false negative scenario where you can't tell the difference between flat bottom transit or two back-to-back flares. But when you have the simultaneous data, that's no longer a concern. Now, Ward, you might be asking, this would all be well and good, but you seem to have forgotten that TESS has only a single wavelength range. It doesn't have a simultaneous UV data set. So how are you going to solve that, huh? So the answer to that question is something called the Early Evolution Explorer, which I'd like to introduce you to. The Early Evolution Explorer, or EVE, will investigate the earliest stages in the shared evolutionary pathways of stars and planets with three primary goals: to detect dozens of planets younger than 30 megayear to assess whether they form water-rich or poor, to determine the effects of flares on atmospheric photochemistry in young planet atmospheres, and also by extension to understand habitable atmospheres, and then three, to understand the effects of accretion on angular momentum transport in young disks, and also ancillary science, including astroseismology of M-dwarfs. The main point is that EVE is a multi-wavelength successor to TESS. It has simultaneous red optical and UV photometry of 10,000 young stars, young clusters observed at 30-second cadence and with 20 to 30-day stare times, and a preliminary aperture, although the design is still being refined, of about 22 centimeters and a 25 square degree field of view. I'll also mention that even though there are three different science cases here, and I'd be happy to talk with you about those during the Q&A or after the talk, I'm going to focus on the one that I'm leading, which is the flare science case. And I'd like to quickly introduce you to our team, our PI Meredith McGregor, and Deputy PI Anne Marie Cody, Neil Turner as a project scientist, and then Jim Burt, myself, and Laura Venuti as science leads, and a large and enthusiastic science team. So in terms of specifically what we can do with stellar flares, right now there are very few observations of flares where we have simultaneous observations in the near UV and in the optical, and therefore the optical to near UV ratio when you move up to flares above about 10 to the 31 to 10 to the 32 ERG, because these events are rare and so they're harder to capture with dedicated monitoring programs. However, there is a trend from Rishi Paul's recent paper showing a slight uptick in the amount of near UV energy at the larger end of their range. And so if this trend were to continue, then EVE would observe a sample such as the one shown with orange. And if not, then it would observe something more like the sample shown in green. And the reason this is important is the red axis on the other side of the plot, where for an Earth-like atmosphere, this different ratio in the FUV to near UV correlated with these effective temperatures would produce several decades of difference in the amount of abiotic O2. And we're still in the process of running these simulations and updating them for other types of atmospheres, but we expect similar kinds of effects, which is why it's important to be able to sample the effects of flares across an energy range and not just at the low energies. So EVE will do this with about 450 flares simultaneously in its first year and hopefully operate for several years. And it'll do this by pointing at the cores of young clusters. So we've identified a number of candidate pointings, such as the one shown here in red, these 25 square degree fields of view for stars that are between 10 megayear and about 100 megayear. And then we're able to essentially go through and compute the predicted flare yields in both bands using the work that we did with Swift and TESS. and find that many different combinations of instrument parameters create a large trade space where Eve would be able to successfully close this particular objective. I'll leave up this slide, and I will also just go ahead and share that we are now past our JPL portfolio gate review. And so JPL is now committed to proposing us to NASA in this year's SMEX call. So we have a lot of work left to do. So if anyone wants to talk more about Eve and TESS, it looks like I'm actually a little bit ahead of time, so I'll go ahead and open it for questions. Sorry, this keep pushing the wrong button.
Excellent. Okay, I was just trying to see what you're thinking about in terms of field of view and finite nerves.
Yeah, the hard part is getting everything into a 150 kilogram package with an affordable bus within 150 to 170 million dollar budget. It turns out that there are cliffs in terms of the bus size, and if you get too much bigger, then it suddenly becomes why don't you propose this as a mid-X kind of issue? So we want to see what we can do within the SMEX cost cap, and it turns out the answer is quite a lot. And I'd love to talk more about our other science cases, such as the exoplanet science case or accretion science case as well.
Jessica?
Thanks. That's what. I think I missed. You said you were going to be able about 30 new exoplanets.
Can you repeat the
Yes.
question, please?
So the question is, are we going to detect about 30 new young exoplanets?
Do you have a simultaneous optical, or I missed that? Are you going to detect the transits in UV?
So we won't be able to detect the transits in UV, but what we will be able to do is detect the stellar flares simultaneously to the transits in UV. The black body of the emission to the flare is extremely strong at the UV wavelengths, and so we're able to show that we can use that simultaneous UV data to say which shapes that we're observing in the optical are due to flare emission versus which are due to planetary transits. So this is the sample compared to known planets.
I have two questions to the same topic. So why using the UVM2 filter on UVOT when you can use the UVW2 filter, which is bluer, more sensitive for your studies? And the second is, are you using the event data for the UVOT time series? Because that can be bent up to milliseconds. It will give you much better time resolutions on the flares. But I don't know if you need that.
So the question, there are two questions. One of them is, why are you using the UVM2 band rather than UVW2? That mainly goes back to photochemistry concerns that we want to probe a wavelength range where we, one, have a lot of comparison data, and two, where it's a lot shorter in wavelength. So even though it's a little bit weaker, it does help us to better understand the higher energy environment, because the closer you get to the FUV, the more connection you should see. The second question, could you remind me again?
So the time series that you show, so the UVT data filter can be connected with the events mode. It's essentially you can spline is a photocounter detector. So you can actually choose your time resolutions.
Mm-hmm.
So have you used those, or you don't need to go to, let's say, 1 second resolution and you just give them 20 seconds?
There's some really interesting physics that you can do at the 1 to 2 second resolution, because that's the native evolution timescale of flares. In this particular project, we were mostly interested in the large scale structure of comparing UV and TESS. And since the TESS data was limited to 20-second cadence, and this was a comparative study, I just went ahead and multiplied that 11 millisecond thing out to about 22 seconds for direct comparison to TESS and used UVOT EVTLC.
Thank you.
Okay. We have time for a very quick question while we change speakers. Please.
I don't know much about this science. I'm wondering why you would expect like a particular temperature black body to work for different flares on different stars. And
so the answer to this is that ever since the 1990s, there's been a lot of optical spectral flare observations from active stars such as 80 Leo or Proxima Centauri, and a large number of these actually are including the great flare 80 Leo. And so a lot of these are actually very consistent with the 9,000 Kelvin black body. And so because empirically it seems to work a large fraction of the time across a large number of stars, it's just sort of been assumed, and it's been extrapolated beyond where the assumption actually holds, which is in the optical observations, mostly small flares.
Okay, let's thank Ward again. Wish him luck. And we have Danica Adams now telling us about photochemistry, which is a good segue from previous talk.
Hi, everyone. My name is Danica Adams, and I'm going into my second year at Harvard now. Today I'll talk about photochemistry at Mars, and if there's time, I'll give you a snapshot of what I do at exoplanets. But feel free to ask me about that later as well. So today, Mars' atmosphere is too cold and thin to sustain surface liquid water. This plot shows the pressure and temperature that you would need to have liquid water, and Mars falls somewhere about here on the plot. And so you have to travel to the further corner of the right side to have liquid water. However, at Mars today, we also see areas on the surface that look like they were carved out by liquid water. So if the atmosphere today can't sustain that, that tells us that long ago, the atmosphere must have been much different than it is today. We think that it probably had liquid water in the very early history, looking back at the Noachian, which is approximately 4 billion years ago. So the main question is, what could have warmed early Mars? Well, first it would need a thicker atmosphere, but what's in the atmosphere is also important. It would need to have a lot of greenhouse gases. And so in 2014 and 2017, folks decided that CO2 with a bit of hydrogen could help warm the atmosphere. But where that hydrogen comes from remained undetermined. A lot of previous works thought volcanism, but volcanism would be by nature very episodic. And so in this paper that I have in review in Nature Geoscience, we investigated crustal hydration as a more sustained source of hydrogen into the atmosphere. In this work, I used a photochemical model called kinetics to learn the lifetime of hydrogen in the atmosphere, as well as other species like CO and oxygen. Then we divided Mars into 2 epochs. We assumed it could be warm and wet at certain times, and we assumed that it could be cold and dry at other times, which are the left and right panels respectively. So when it's warm and wet, if you have liquid water, that liquid water will react with the reduced iron in the crust, and it'll suck out OH, as well as water. And so since there's more than one hydrogen on water, that will release hydrogen into the atmosphere. That hydrogen can then diffuse upward and escape, which is on the right side of the panel. That's not the only hydrogen in the atmosphere. You can also photochemically form hydrogen by splitting apart water through sunlight, and that will go through this Hawk's chemistry to form hydrogen over there. I then coupled this to a climate model called Red Fox to re-examine the importance of hydrogen in these different climates. On the left side, however, Mars can't always be warm and wet, so we also investigated what happens when it's cold and dry. In this case, the reduced iron is exposed to the atmosphere, and oxidants like oxygen are sucked out of the atmosphere into the ground. And as I'll show soon, this causes a CO runaway because the photolysis of CO2 is now not balanced by this Fox reaction because you're losing a lot of oxidants. But I'll first show results for the warm climate. So in warm climates, if you look at the plot on the top right, I'm showing the mixing ratio of different species as a function of altitude. And the colors represent different fluxes of hydrogen coming from the ground from that crustal hydration. In the upper inset, you can see the surface temperature is only warm in the red and yellow cases, which are the cases where the hydrogen flux is greater than 10 to the 12 per centimeter squared per second. Now, I know that unit probably sounds like nonsense, but we can do some back of the envelope estimates to figure out how much water you'd have to lose to sustain that hydrogen. So based on surface measurements, we estimate that up to 400 meters of a global equivalent layer, so if you cover all of Mars with water, that's how deep that ocean would be, just as a volume of water. So that much water could have been lost to crustal hydration, and a comparable amount could be lost to iron oxidation. And so if you sum all of those and then compare it to the flux, you ultimately find that Mars could be hydrogen rich and warm for only up to 40 million years total. So that's not a large fraction of Mars history. Also, in our photochemical model, we can learn the lifetime of hydrogen, which is this lower panel. And it shows that it takes hydrogen about 10 to the 5 years to respond to any changes. So we know that each warm episode must have been at least 0.1 million years. So now we've constrained how long Mars could have been warm, and roughly how long these episodes could have been. But again, not always warm. So in cool climates, we might have different chemistry because now you're losing those oxidants out of the atmosphere. And so here I'm showing the mixing ratio of CO and CO2 on the left axis there. And you can see that it takes a very long time, but if you wait long enough, the CO starts to swap places with the CO2. So after about 10 to 7 years, you end up with this CO runaway. In my undergraduate, I have a paper in Correct for Resolution, which shows that some uncertainties in Hawks may actually drive an even greater CO runaway than my original paper estimated. So to recap at about the halfway point, there are 3 early atmospheric redox possibilities. First, Mars could be warm with a CO2 and hydrogen-rich atmosphere, and that would last for anywhere from 0.1 to 40 million years. Also, Mars could be cold, and when it's cold, if it's been a short amount of time that it has been cold, then the CO2 in a low hydrogen state could last for less than 10 million years. But if you're cold at early Mars for a long time, you'll end up in the CO runaway state, and that might last for more than 10 million years. So now the question remains, first, how could you transition from cold to warm? And second, is there any evidence for this, or am I just making stuff up? So first, folks have investigated the idea of alternating climate states and also redox states. So volcanism and also changes in the obliquity are known to modify the redox content of the atmosphere. But in addition, my undergraduate Kaya Thomas, shown there, is investigating whether hydrocarbons could help warm up early Mars. If you form too many hydrocarbons, you end up with a soot-like haze and that'll cool you off. But as shown in previous works for early Earth, if you have a high amount of nitrogen, you can form some hydrocarbons with a lower amount of haze. So she's still trying to find the sweet spot for early Mars, if there is one. But most importantly is whether there's evidence for these changes in redox over time. So with the Mars MSL, Mars Science Laboratory, today, we've already found species in the soil. These are volatiles, where they scooped up soil with their instrument, baked it and heated it up, and watched these volatiles pop out of the rock. And these are very different redox states. We have very oxidized and very reduced things. Now, I'm not saying you can't form reduced species in an oxidized climate. I'm sure you can. But what's interesting is to find out whether you can form this ratio of oxidized to reduced things in different redox climates. And what's even more interesting is that with Mars sample return, we'll soon be able to do even more sophisticated analyses of the isotope measurements. So today I'll show you predictions of why MSR is so important to understand Mars climate over time. So first, going into sulfur. If we look at sulfur at Earth, you'll see that the fractionation of the isotopes is quite variable over Earth's history. You'll see a lot of fractionation in the isotopes, and then once you hit the great oxidation event, where oxygen just plummeted into our atmosphere, then the fractionation goes away. And that's because of the shielding effect, where SO2 photolysis will fractionate the isotopes, but oxygen and ozone also go off the same photons. And so if you have a lot of oxygen in the atmosphere, the fractionation will be low. And so what I've done is I've added sulfur isotope chemistry to kinetics. My undergrad helped adapt the Venus chemistry over to Mars, and then I added the isotopes in and validated it. And we found that the SMIF is important to determine the redox. And so in this plot, I'm showing you the mixing ratio of different species as a function of pressure. And you can see that the amount of sulfuric acid is different for the different redox cases. So the solid line has no hydrogen, and the dotted line has a lot of hydrogen, and so you can see the oxygen does the reverse of that. And then over on the right, I'm writing the 33S enrichment compared to 32S. And as we would expect, the case with no hydrogen or a lot of oxygen has the least amount of fractionation. In the case with the least amount of oxygen has more enrichment of the heavier isotope. So with Mars sample return, we'll be able to compare to this modeling effort and determine what the redox might have been at certain times. Sulfur is not the only interesting isotope. There's also nitrogen. So in the NOx family, you can form nitrates from either solar energetic particles or through lightning. In two recent works, I found that in a warm climate, you would form more nitrates, but in a cold climate, you would form more nitrite. There are some ways that you could back this out with the current measurements we have, but it's really tricky. And so with Mars sample return, it will be easier to learn if you have nitrate or nitrite in the soil versus just some NO. And so if we were to couple that with the knowledge of fractionation of nitrogen, we could then determine when it was cold or warm at a different time, because the nitrogen fractionation is quite low when you deposit nitrates, which means the actual act of depositing nitrates doesn't change the relative amounts of the isotopes. That's what my undergrad Julian Shawcross has found, and I co-mentored him with Mike, who's going to talk next. So the fractionation of N15 does not change much when you deposit nitrates, which means that this ratio should track closely with atmospheric escape, or also over time. And so if we know nitrate versus nitrite, and we know when it was formed based on the isotopes, that will also give us a constraint on the climate. My last set of isotopes is the oxygen isotopes. Again, comparing back to Earth, the oxygen isotopes will get fractionated in a warm climate based on evaporation and condensation. But also they get fractionated quite strongly by stratospheric ozone chemistry, which is what I'm showing here. In this panel, I'm just showing the ozone chemistry, and you can see that H2O2 and ozone are quite fractionated. And so with MSR, if we were to have maybe ice cores, of course, it's hard to keep those frozen on the trip back. But if you could get ice cores and measure these levels, that would also give us better constraints. In my 1 minute remaining, I'll give you a teaser on bonus science. A lot of this relates back away from Mars and over to exoplanets. So with the S chemistry, I've brought it to early Venus-like worlds. O chemistry, we're studying snowball Earth. In N chemistry, I have students working on early Earth-like worlds. So feel free to ask me about these projects. This one is looking at hazes and how they could cool off early Venus. This one is looking at snowball Earth using O isotopes to determine whether there was any exchange between the atmosphere and ocean. And in these two papers, we're looking at N fixation at early Earth and then exoplanets of different pressures. These are the works that I've presented and that I've been working on this past year. And I will stop for questions. Thank you.
Questions for Anka? Yes.
So it's really interesting. This is not at all my field. But when you're talking about these isotopes, measuring these isotopes in the soil and Mars, does it matter the assumption that you make about, for example, like the meteor impact history and how that leads to the composition of the soil that you're actually measuring? Does that matter?
That's an amazing question. I think we would probably, well, this is also outside my expertise. I don't usually do the measurement. I think if a meteorite had hit Mars, it would probably leave a crater, and so we probably know that material might have been influenced by one. So hopefully we wouldn't be too near it. But if you're like Gale crater, it might be harder to tell if it's from Mars originally. I think a good test might be like the gas bubbles is how they determine if it's like a Mars meteorite when it hits Earth, is to see if the bubbles match the atmospheric composition of Mars today.
Thank you, Danica. This is really awesome. I was wondering when it comes to these isotope modeling, looking at like sulfur versus nitrogen, at some point, do you have a model that can sort of put all of them together, or is that like, I'm sure it's like super hard to do, but I was just wondering if looking at interdependencies with all the species included, if that's something down the line would be possible, or maybe it's already included to some extent.
That's an amazing question. I will say that kinetics is a nightmare to work with, and so right now I'm working with just CHNO chemistry plus one extra guy. But I think it would be interesting, especially like sulfur and chlorine interact a lot, and nitrogen will affect O isotopes. So I think there is a lot of interdependencies there, but I personally hope to stay away from that as long as I can.
Last question.
Great.
Can we get the next speaker also?
Oh.
Yes, please.
Yeah, so I was wondering if this has any relationship to recent results from MAVEN and the Hubble Space Telescope on measuring the rates of escape of deuterium and hydrogen over time as a measure of where the water went up from Mars. You know what I'm talking about? Led by Professor Clark at BU.
Yeah, there's two relevancies. So first, looking at the data H, you can back out how much water escaped from Mars over time. And we find that it's a substantial amount, but it's not enough to explain, well, it's on the lower limit to explain like geology. And so that's why we think some water must have gone into the crust. And then looking at the other like isotope measurements or modeling that I'm making, these species probably wouldn't escape in the same way that hydrogen does. Hydrogen escapes more thermally, whereas these are heavier, and so they would escape more from like sputtering. But MAVEN has made some important observations of argon escape, actually argon isotopes, to estimate the rate of sputtering, and that's really relevant to figure out how these isotopes would change over time.
Okay, great, thank you.
Thank you.
Let's thank Danica again. Now we have Mike of some student-led projects.
All right, thank you. It's such a pleasure to be speaking right after my good friend and colleague, Dr. Danica Adams. And I'm Mike Wong. I'm a third-year Sagan Fellow. And today I'm going to be talking about student-led projects at the Astrobiological Frontier. So one of the best gifts of the NHFP program is the ability to do the science that you love with the people that, really inspire you. And for me, those are the students that I get to work with. They're just simply amazing, and they share my passion for astrobiology. And so it's just been such a gift to have the freedom in this fellowship to be able to mentor so many amazing people. And in this talk, it's going to be dedicated really to 3 of the students that I've had such a joy and pleasure and privilege to be able to mentor over the past couple of years. So we're going to be meeting Maddie Christensen, who is a senior here at Caltech, Lucas Pfeiffer, who is a graduate student at the University of Washington, and Emmy Slaughter, who is a junior at the University of Florida. And they've all been instrumental in making great advances in the fields of the origins of life, planetary habitability, and our search for life in the universe. So because time is short, let's just jump straight into Maddie's project. Maddie simulated nitrogen fixation on early Earth to try to set the stage for life's emergence. She did this under the mentorship of myself and Danica, who just spoke, as well as in collaboration with Patrick Dunn at UC Berkeley and Yuck Young, a professor here at Caltech. This was published earlier this year in the journal Life. So why is nitrogen fixation important? Well, mainly it's because of its role in the origins of life. So one of the leading hypotheses for the origins of life on our planet situates our emergence at the bottom of Earth's Hadean Ocean, roughly 4 billion years ago or so, at what are called alkaline hydrothermal vents. And in these geochemical scenarios, we have 2 powerful sources of disequilibria, or free energy, that's thought to be instrumental at sparking metabolism into existence. We've got this steep pH gradient between the acidic and the alkaline fluids, as well as this redox gradient between the CO2 and the nitrate and the seawater, and the hydrogen and methane bubbling up out of these vents. And so nitrogen oxides are thought to be very important to this scenario because in a time before there was a lot of oxygen, O2, on planet Earth, these nitrogen oxides could serve the role of a very high potential electron acceptor in this redox gradient, as well as giving a source of nitrogen, accessible nitrogen, or what we call fixed nitrogen, to early metabolism. So our modeling project actually included 4 different models. One, a thermochemical model to model the production of these chemicals through lightning, a solar energetic particle model for the early sun, and then the photochemical model kinetics, which Danica introduced us to in the previous talk, which simulates a host of chemical reactions within the atmosphere. And then we have a very simple equilibrium chemistry model for the ocean to find out the final speciation within Earth's early ocean. And so, jumping straight into some of the results from Maddie's project, what you're looking at here are the lightning-induced fluxes of nitrogen oxides and hydrogen cyanide. Hydrogen cyanide, there's a whole other prebiotic chemistry story there that we don't have time to talk about, but Maddie modeled both of them. And this is the nitrogen oxide flux in blue and the HCN flux in red as a function of our general uncertainty with regard to the chemical composition of Earth's early atmosphere. We're not sure exactly how much hydrogen or methane there would have been on Earth's early atmosphere, as well as the overall pressure, which is what is responsible for the sort of variation in the vertical regime here. But you can see that somewhere of order 1 by 10 to the 8 molecules of nitric oxide per centimeter squared per second were produced via lightning on early Earth. And then we plug that into our photochemical model and our oceanic model to arrive at the final oceanic concentrations of these nitrogen oxides. Here, nitrate shown in the purple, as well as HCN shown in the green. Again, as a function of our uncertainty with regard to the chemical composition of Earth's early atmosphere. And here, the 3 different panels represent 3 different pressure regimes that Earth's atmosphere would have gone through during the Hadean. So the upshot is basically that of order 10 to the minus 9 to 10 to the minus 8 molar concentration of nitrogen oxides is expected in the bulk Hadean Ocean. Now, why is this number important? It's important because it helps inform our experimental colleagues, like Dr. Lori Barge at JPL, where she tries to create the hydrothermal scenarios that we're interested in for the origin of life on her benchtop. And so our theoretical work can really help her constrain the kinds of chemical parameter space that would have been relevant to the early Earth. And so, for instance, Lori had a landmark paper in 2019 showing that you can aminate, which means add some nitrogen to pyruvate to create alanine. Alanine is one of the 20 essential amino acids for life on Earth. So there's a really rich theoretical and experimental synergy here. So to summarize Maddie's contributions to astrobiology, we know that protometabolic systems may have been driven into existence by chemical disequilibria at alkaline hydrothermal vents. These nitrogen oxides could have contributed to emergent life by serving as high potential electron acceptors to kickstart metabolism, as well as sources of accessible nitrogen to biology. And there are deep implications here for the origins of life experimental work that comes from theoretical modeling such as this. Now, the Earth's early rock record doesn't really extend very far back into the Hadean epoch because we have this thing called plate tectonics, which recycles rocks. So how do we know that something like this actually occurred? And Danica gave us the answer in the last talk, which then we can look at Mars, which lacks this kind of crustal recycling and preserves stories from 4 billion years ago or so all over its crust. And indeed, we find roughly 100 to 1,000 parts per million nitrogen oxides in its crust, likely formed during some period of time when Mars was warmer and wetter and had these same types of processes occurring that would have created these chemicals. And so that discovery from the Mars Science Laboratory inspired Lucas Pfeiffer and I to try to model an early Martian metabolism for hypothetical life on early Mars called nitrate-dependent iron oxidation, with implications for the interpretation of the organics that are found at Gale Crater. So this NDFO metabolism would have been a very plausible metabolism for early Mars. Basically what it does is microbes here on Earth that perform it take nitrate and turn it into N2 while at the same time oxidizing iron. And so we thought we'd just do a thought experiment. If there was this kind of ecosystem on early Mars, it seems like a very plausible kind of metabolism to run, how much of that life could be there? And then how does it compare to the amount of organics that we actually have discovered at Gale Crater? And so to summarize the approach to this modeling project, we take the nitrogen oxide rainout rate from Danica's brilliant 2021 paper and use that to estimate the available Gibbs free energy of this environment. How much energy was there for life to take advantage of? With that available Gibbs free energy, plus some assumed biological efficiency, we can estimate the size of the microbial community. And then with that microbial community, plus a host of factors that influence the organic preservation in Mars through time, we can then estimate the preserved organic concentration that we would expect to be left over by that kind of ecosystem. Now, everything that you see here in a white box is a free parameter in our study. There are wide uncertainties for each of these processes. And so we do a Monte Carlo approach, have thousands of different hypothetical Martian ecosystems. And through comparing to the measurements of the actual organics that we find at the sediments of Gale Crater, we can constrain something about this hypothetical biology, in particular, the efficiency and the cell turnover rate. So the first major finding of this study is that the amount of organics that life could have produced on early Mars vastly outweighs, by orders of magnitude, the organic concentration that we actually find in Gale Crater Lake, which in turn outweighs the amount of organics that were delivered through meteoritic infall. So in other words, there was abundant free energy on early Mars in the form of this nitrogen oxide reduced iron redox couple. Another way of putting this is that we can constrain the overall abundance of life on early Mars based on the little amount of organics that we actually find to a cell density of less than 10 to the power 7 cells per liter. This is a few orders of magnitude smaller than the cell densities in Earth's modern oceans, but is consistent with the cell densities that you would find at Earth's subsea floor. And finally, we can also constrain the biological efficiency of these organisms to less than 5%. In other words, life would not be limited by free energy, but something else in the Martian environment, some other key nutrient, and we hypothesize that that might be phosphorus. So to summarize Lucas's contributions to habitability and biosignature preservation on Mars, number one, we find that meteoritic infall cannot explain the abundance of organics at Gale, so there needs to be some other input of organics. That could be through photochemistry or hydrothermal activity, or by putative Martian biology, and that's the hypothesis that we investigate here. We find that there's abundant free energy on early Mars in the form of these nitrogen oxides and reduced iron, and that life would likely not be limited by free energy, but by some other key nutrient like phosphorus. And that if life did exist on early Mars, we can cap the cell density of that ecosystem to less than 10 to the power 7 cells per liter. Again, that's much smaller than the cell densities in our modern day oceans, but is consistent with what we find at Earth's subsea floor. So now that we know that early Mars could have had plentiful life, it's time to go and see if we can find that life. It's time to develop novel in situ biosignature techniques for solar system exploration. And this is a project that I've been working on with Emmy Slaughter. So last year, I introduced you to my best friend, the pyrolysis gas chromatograph mass spectrometer. If you've forgotten what that is, or if you're new here, basically it is a very fancy oven that not only bakes your sample, but tastes it for you too. This is the kind of data that the pyrolysis GCMS gathers, a forest of peaks. Each peak represents a molecular fragment in your sample. This particular pattern represents typical Earth bacteria. We also have a host of diverse other kinds of samples, plant matter, aged organics like petroleum, and then carbonaceous chondrites as well. And we were able to train a machine learning algorithm to distinguish biotic and abiotic samples with an accuracy of 90%. That was the punchline from last year's talk. So what's new? Well, our algorithm was trained on pure samples, purely biotic or purely abiotic. So the big question now is, will our machine learning algorithm be able to detect the presence of life in heterogeneous samples, samples that are mixtures of biotic and abiotic? Again, this is important for the search for life on Mars because Mars's surface is coated with meteoritic infall, organics from space that have nothing to do with life. So if there is life on Mars, it would be mixed with those organics. Can we actually find that signal hidden in the abiotic noise? And so that's what Emmy spent the summer doing at Carnegie. She was mixing a bunch of abiotic and biotic mixtures. For our abiotic component, we used synthetic insoluble organic matter, which is a meteorite substitute because meteorite powder, it turns out, is very expensive and hard to come by. So we used the synthetic substitute. And then all different kinds of life. We've got eukaryotic life, bacterial life, archaean life, and even fossilized life in the form of this metasequoia, roughly 45-million-year-old fossil wood. And Emmy made all sorts of different mixtures of different combinations and different ratios. And to jump to the punchline, what we found is that in mixtures with those aged biotic samples, with those fossilized life, we found a detection limit for our machine learning algorithm somewhere between 10 and 30%. So there's this vast range of true positives where the algorithm is successfully able to detect the presence of life, and then this region of false negatives where the algorithm did not find that that was a living sample. Mixtures with the fresh biotic samples, turns out the machine learning algorithm was much more successful at finding the living signal here. We haven't reached the detection limit yet. It's somewhere between 0 and 10%. We do know that it has to exist because the algorithm successfully detects a purely abiotic sample to a high degree of confidence. And so to summarize Emmy's contributions, she investigated a robust agnostic biosignature technique based on pyrolysis GCMS combined with machine learning, and found that the technique is capable of detecting trace amounts of life against the background of abiotic organic molecules with a detection limit of somewhere between 10 and 30% for aged biotic matter and less than 10% for fresh biotic matter. This has deep implications for our future astrobiological missions and interplanetary sample return if Mars sample return happens not on all of the aged biotic wood. So to summarize the contributions, we've got Maddie Christensen, Lucas Pfeiffer, and Emmy Slaughter, who have done amazing work at pushing the frontier in the envelope of astrobiology. It was a great privilege to be able to guide and mentor these rising superstars, and I can't wait to see what they do next. Thank you very much.
We have time for one question. Yes.
So this is really awesome. So I was wondering, you know, are you sensitive also to other processes of biological nitrogen fixation potentially on early Mars, things like pre-living fixation in the soil as well?
So the question was, are you able to be sensitive to the nitrogen fixation from biology on early Mars?
Yeah, the products, similar to, you know, the processes that you're testing for products coming out of nitrogen fixation in biology and water.
Yeah.
You know, there are other processes like in soil, like protein soil as well. And I wondered if you were sensitive to those differences.
Absolutely, and this ties back into the project that Danica spoke about very briefly with Galen Shawcross, who's a junior here at Caltech. He's investigating the nitrogen fractionation of isotopes that we would expect purely through abiotic mechanisms. And if we go to Mars and we're able to make that nitrogen isotopic measurement and find that it deviates wildly, right? Life usually tends to prefer the lighter isotope. We might be looking at some kind of evidence of biological nitrogen fixation on Mars.
Let's thanks Mike again. And let's welcome, last but not least, Ryan McDonald. He's going to tell us some exciting news about JWST and the purpose of studying rocky worlds.
Okay, thank you. Hello, everyone. I am Ryan McDonald. I'm going my third year as a Sagan Fellow now at the University of Michigan, and we've heard a lot of really great talks already about rocky exoworlds. So let's now take a look now at observational evidence searching for atmospheres on rocky exoplanets. Because of course, one of the big fundamental questions that we have is what is the underlying diversity of atmospheres on rocky worlds around other stars? And at the moment, with the capabilities of JWST, we're principally focused now on searching for atmospheres on rocky planets orbiting M stars. We'll have to wait for habitable worlds in order to go to sun-like stars. So during my PhD, I was very focused with good old Hubble and ground-based telescopes on characterizing the atmospheres of giant planets, hot Jupiters and Neptune-mass planets. But now we finally have the observational capabilities to push down to rocky worlds. So we've heard about a number of techniques already to search for atmospheres. What I principally use is called transmission spectroscopy. Essentially, we measure how the effective cross-sectional area of a planet varies as a function of wavelength during a transit event. So that's what we can see over here. And we know where the absorption features of the various molecular molecules are from first principles quantum mechanics and laboratory experiments. So when it comes to knowing where to search in parameter space for atmospheres on rocky planets, we're fortunate in that the solar system already gives us some clues. So in this framework that has been called the cosmic shoreline by Kevin Zarnley, you can see that as a function of the escape velocity of objects in our own solar system and the insolation that is received, there is a corner of parameter space with high escape velocities relative to the insolation where we see thick atmospheres like Earth and Venus, while more tenuous atmospheres like Mercury up here, or even just rocky bodies that have no atmosphere or up in the top left. But what we don't know is how this generalizes when we change the star. How much of a fundamental universal principle is this cosmic shoreline? But what we can do is use this in order to choose which exoplanets we want to observe in order to search for atmospheres based on a probabilistic argument of how plausible a thick atmosphere would be. And that is what we have been doing. I'm going to be talking in this talk about 3 case studies of planets that I've been involved in the modeling efforts of over the last year, 2 of which come from a large Cycle 1 program led by Jacob Osterjager and Kevin Stevenson. And then the third planet I will talk about is from a very recent DDT proposal that we put in. So the first 2 planets that I will discuss from the Cycle 1 program are kind of just straddling the boundary of the cosmic shoreline, a little bit into the regime where we would not expect there to be thick atmospheres. But the third planet is way off the y-axis there, in the regime where we do expect a thick atmosphere. Okay, so these 3 planets have a wide array, so we're going to first initially start off with a kind of Venus surface temperature object and gradually push down in temperature to a planet in the habitable zone. But I know that all of these planets are larger than the Earth, so they're in a more interesting regime than the rocky planets we have in our own solar system, a very unique regime. Okay, so let's start off with GJ486b in a paper led by Sarah Moran, who is here today. So we got some beautiful observations from 2 independent transit observations with JWST with the NIRSPEC G395 instrument that you can see here. When we convert that into a measurement of the transit depth, how the depth of the transit varies as a function of wavelength, what we're seeing is very consistent results regardless of how you kind of detrend and analyze the data. And what is exciting is that you might notice even by eye that there is a sloping trend that we can see there. So if you just fit the data without invoking an atmospheric model, just with like a Gaussian model, we see that this is a deviation from a flat line at roughly 3 sigma significance when we do a Bayesian model comparison. And that is exciting, or at least it gets theorists like myself excited. What can explain the deviation from the flat line? And one of the very first models that we tried invoked water absorption from an atmosphere on this planet. Because essentially there is a water absorption band at 2.5 microns. So if you see half of the water band, you can produce this slope. So at this point, this is how I was feeling. Okay, great. Have we got an atmosphere on a rocky planet for the first time? Well, then I decided to try and disprove this because it's a big claim. It's a really big claim if you want to claim an atmosphere on a rocky planet. So very quickly, we established that actually there is a degeneracy here. If you have no atmosphere on the planet whatsoever, but you have unocculted star spots on the host star, for a reason that I will show in the next slide, we can essentially get ghost absorption features shown in this orange model here, which is still caused by the presence of water, but it's water in the star spots themselves and not coming in from the atmosphere of the planet. So how does this happen? Well, essentially, the planet is transiting across a specific region, a transit chord of the host star. And the spectrum that is impinging on the atmosphere of the planet during a transit can be different than the integrated average spectrum of the stellar disk. And this difference in the light we see from the star as an average and the light shining on the atmosphere can propagate forward into our models. So if there is a big difference because we have a very spotty or with hot active regions like we heard from Ward earlier, then this can cause absorption features that are not actually caused by the atmosphere. And we call this the transit light source effect. And so in short, we have two different explanations here that are degenerate over this wavelength region, but are not degenerate when we push to shorter wavelengths. Because then you can start getting features like titanium oxide, vanadium oxide bands from the host star that cause a deviation here. So next summer, a team that I am leading will be obtaining 3 observations with the NEARES instrument on JWST to obtain these short wavelength observations, break the degeneracy, and establish whether or not this is an atmosphere or caused by star spots. Because if it is an atmosphere, as you can see here, this is the amount of water in the atmosphere. So the best fit is almost a 100% water steam atmosphere. So it would be really cool to know if we actually have a steam world for the first time. So that's our first planet. Let's jump now down to a slightly cooler temperature planet, GJ 1132. We also observe this through the same JWST Cycle 1 program. So this planet has been interesting for many, many years. So in this was actually a set of Hubble Space Telescope observations that were used back in 2021 to claim a potential hydrogen-rich atmosphere with hydrogen cyanide, potentially indicating a primary atmosphere with volcanic outgassing. But this was a very controversial result, and subsequent analyses, reanalyzing the same data, found instead a flat line without any absorption features. So the Hubble data was contradictory depending on how you analyzed it. So we set out to observe this planet with JWST to establish if we could see any signatures, in particular of gases like hydrogen cyanide. So we followed the same observational strategy, 2 transits with the JWST NIRSpec G395 instrument. The first transit that we attained was pretty exciting. Again, we saw a slight slope towards the short wavelength and maybe also an absorption feature at 4.5 microns. So we were getting pretty excited, dusting off our first models, but then we made the mistake of observing the planet a second time. And we got a completely flat line. And this is also a 3 sigma deviation from flatness. So this was a very strange thing to actually see. So we ultimately decided to analyze each observation separately in order to illustrate how important multi-transit repeatability is when claiming an atmosphere on a rocky planet. Because if you just analyze the first observation, you find the best solution is a near pure water atmosphere on the planet with a trace amount of about 1% of methane in the atmosphere. Or you can explain it also by unocculted star spots. But the second transit, completely flat, so you don't need an atmosphere, you don't need star spots at all. We're still investigating reasons that could cause this discrepancy. We've actually observed this system 2 more times, and we're currently working on analysing all 4 of the transits combined. But what this does illustrate is perhaps a really important thing, that if you want to make a claim of an atmosphere on a rocky planet, if you see any signal, after you've been able to show that it's not coming from the star, you still need to show that it is repeatable, and ideally across multiple different instruments. Okay, so now in the last few minutes, let's look at this planet in the habitable zone, LHS 1140. So this planet is way over here. Of all the currently known transiting exoplanets, it is the one that is the most likely to hold on to a thick atmosphere. So we really should expect to see something here. So we observed as part of a director's discretionary timing proposal that we submitted with the nearest instrument, now at shorter wavelengths than the previous observations I was showing, to break the degeneracies with star spots. First, we found that at the shortest most wavelengths, we see these inverted features here that are caused by stellar contamination from unocculted hot facular regions on the host star. But what is exciting is that when you do a simultaneous fit of the stellar contamination and the atmosphere, one of the big puzzles here comes in here, that the best fitting scenario wants to put in a huge amount of nitrogen in the atmosphere. And I should say as well, these 2 visits were completely consistent in the stellar contamination that we observed, so we were able to combine them together this time. So let's zoom in and examine where this is coming from. If you divide out the stellar contamination signal from the spectrum, this is what we see. So if you just have a model that is entirely characterized by the host star, it should be a flat line here. But we find that our best fitting model has a slight slope towards the short wavelengths that is beautifully fit by an atmosphere that is rich in nitrogen, 100% nitrogen, which, if confirmed, could genuinely be a signal of an atmosphere much more similar to our own Earth. But this needs to be confirmed. It's only about a 2.3 sigma preference, and we're worried as well that it could be deficiencies in our stellar model that could be explaining this. So this is just tentative at best. But you can imagine what I'm going to be busy doing over the next few weeks, getting ready for the JWST Cycle 4 deadline. And this is a beautiful artist concept we put together showing our interpretation. If there is no atmosphere on this planet, we've essentially got a scaled up version of Europa, a giant ball of ice, because the equilibrium temperature is about 200 or so Kelvin for this object. But if the nitrogen-rich atmosphere is real, and there's a sufficient amount of carbon dioxide in the atmosphere, we expect there to be an ocean roughly the size of the Atlantic Ocean at the substellar point, the center of the day side, with a cloud deck above it in this artist concept. So with that, I will leave up my conclusions. We're starting to get some really tentative signs of potential planets that could have atmospheres. They still need to be confirmed, but the fact that we can even do these measurements with JWST is incredibly exciting. Thank you.
For GJ1132b, when you have 2 different transmission spectra, a flat one and then one that may be consistent with stellar activity, where in the stellar rotational phase were these 2 transits observed? Like if there was a large spot that rotated into the field of view and you get contamination that rotates out and it goes flat, would something like that be possible?
Yeah, so that was the first idea that we had to explain it, just stellar variability, but it was, I forget the exact number of days apart. Well, I do actually have that there. But in short, we don't think, there you go, because you see it's only 10 days apart. So we don't think it's caused by that, because we also observed the total spectrum of the star itself outside of transit, and we don't see any variability in the overall stellar spectrum itself. So it can't be atmospheric variability. We can't suddenly have the whole atmosphere being cloudy. It can't be stellar variability. So we think it's either going to just be an unlucky random noise draw or an instrumental systematic that we don't currently understand, but we don't think it's inherently astrophysical variability from the start.
Yes. Yes,
Oh, that was my question.
please.
Yes. So this stellar contamination hypothesis, is this like a small number of big sunspots that are stellar spots or many small ones?
It could be either, because you just need it's just the integral of the stellar disk that is not a quarter during the transit. So we just fit for the overall integrated covering fraction of the host star that is composed of heterogeneities. But we are assuming that they have the same temperature in this particular case. But yeah, we can't really differentiate between the size distribution.
This last
What
one.
is the temperature of the steam planet?
Oh, the temperature of the steam planet. The equilibrium temperature is about 700 Kelvin for the first planet and about 500 or 600 for the second, and the retrieve temperature that we get out is around about 600, 700 Kelvin or so.
You see, so it's very high temperature.
Yeah, definitely not habitable.
Okay, let's thank everybody from this session.
Yeah, I got
40.
340. 340, yeah.
I was looking at
Nope, we got everyone in. Officially. Yeah, go ahead and click through to the shirt column.
it's not storage, but
It is open anything. Cool.
Yeah.
Great. Yeah, good luck. Microphone's off right now. On it. This one is on, but no one.
This one's better, but nobody's gonna be
Really talking.
Yeah.
But just it's easier, I think.
Yeah, like $2 from the hotel. I would think they would want our.
Yeah, it's not clear, you said it wasn't there, it was going to be activated, but. Probably goes
What? I thought you were all over Slack. What, you were reading plenty of slides in person?
Well, the first time I was.
Yeah, you're. Right.
Yeah, I'm gonna do the same thing.
Okay, yep, no, both of you can, I just need to figure out if.
I didn't want to be surprised and have like a video not play or something.
Yeah, exactly, right, I think we downloaded them all. Okay, so here, so find. Right.
But I can't.
Oh, no, you're right, yeah.
They can't use the baby back.
Even beyond that.
So, oh, yeah.
Yeah, I don't know if I'm set up. Yeah, no, I don't think I ever.
Yeah.
Somehow.
Don't worry about the caption. Okay. Oh, okay, that's just it. It's just. So,
So CBS is.
yeah, I think that.
Like, we get a 5% discount.
Okay.
You're welcome.
And then you actually cross that kind of second column. Like we run a lot of Phoenix models, but then, and they'll be also be hard to like this.
Just check this. Good. That's doing what it should do.
There you go.
I just really like stars, and I'm sorry for you guys, but I'm really glad that this makes my life a lot more fun.
I think everything looks good.
Awesome.
Good. I was worried, so I think it's like, it's Mac to Mac, so it works.
Yep.
I don't know if you've noticed this, that if you do Mac to Windows, PDFs don't show up. There's information, yeah, if you have PDFs embedded in your PowerPoint, information just disappears.
Huh, okay.
I had a figure once that was just C's and all the data was
Oh, well, that's good. Then you get to describe it.
Exactly, draw.
Use your imagination. Thank goodness, you're welcome. Yeah, I just helped two people check theirs, so it's fine, and that seems to be okay. I only have one more session. Right?
The clicker?
So, yeah.
Yeah, and it charged over lunch. So I'd be very surprised if there was something wrong.
Yeah.
There better not be, I'd be
No,
furious.
I know. Yeah, very strange stuff. Okay, good. Any more thoughts? And people seem to be happy, so let's.
That's what the 7 comes for.
To
To always be, I could tell someone was in here messing around with the presentation because I checked the lights. I was out being quickly, it was like, something's going on.
Yeah. Okay, sorry. Yeah, usually, this is your first conference, but it's like, yeah, usually, folks come out.
There's always something that goes on. We're down to only 2 people on the line today.
Okay.
This morning you get on. Oh,
Wow.
and then I quickly felt like, we're gonna convert 2 people on.
Yeah. I mean, you know, the fellows in this one, they have to. Because this is a, you know, this is taxpayer money, that's, you know. There's a bit of,
So, I'll be here Thursday from my neck to support you. I assume you will also join soon, then we can make you to be the meeting host.
Yes, I think that's how it's working right now. Yeah, that's exactly it. Good. Seems to be going okay for now.
Okay. Wonderful.
You'll be here Thursday.
Thursday.
Yeah, you can work that out.
Okay,
I'm planning to be in that line.
okay, okay, good. I think Wendy told us to be here at 9:30.
It's fine. Yeah, I might have to do some
Yeah. Yeah, that will probably stay here the whole time. Yeah. Good.
Yeah, if
Yeah,
everything is like.
and you're charging it, so it's fine.
If everything's still just around, a week, then we're gonna be probably filming. Got it. All right, cool.
Okay.
Sounds good.
Okay.
Speak too soon, but
Live stream is on.
Yeah, yeah. I love the debating timer. It's so nice. Especially like as a moderator too, it's just trying to wave at people.
Did you test your slides and everything? Or
Yeah, yeah, I think it's all good.
And like for the Zoom, like your screen sharing and
Yep.
we just
Are
gotta
you-
double check that.
You're
for-
sharing.
Yeah, I'm sharing.
Okay, you've got a big old clock behind you. You just,
I just like all this.
you just tap it to start, you know.
That's great. That's very convenient. Thank you.
It's excellent. There's my mouse.
Yeah, and my Zoom person is, let's see, Maggie Thompson, who spoke earlier today.
For the most part, I think they're just looking at the chat to see if any questions come in.
Yeah. No, but that's what Maggie's doing, right? Okay, good.
Yeah, you should.
I was like, I've got to watch the clock and the person.
Yes. Also, so a tip with the timer, when I was moderating earlier this morning, I found it was easiest to just let it keep going during questions because it'll keep counting up as like overtime, but that will tell you how much time is left. Yeah, like, because there's 3 minutes for questions and switching, but there's no reason to like stop the timer, go to a 3-minute timer, like just let it keep going.
I see what you mean. I see what you mean. That's a good tip. That's a good tip. Yeah, we haven't talked in a while. How's everything going at the CFA? You're also at the CFA. So you're at the CFA. Half the room is at the CFA.
CFA people, yeah. I think a lot of us were on the same flight.
We all
today too. Yeah.
Oh yeah, the one in the morning. Like I realized I saw some familiar faces.
Yeah.
I saw like Michael.
Yeah.
Yeah. So you all were on the same flight also?
Yeah, I'm pretty sure.
I was on the same flight also. Cool,
Yeah.
cool.
It's good.
Yeah.
How's MIT?
MIT's same old, with all its quirks.
Some complaints.
No, it's okay. Overall, it's they treat the fellows there really well.
Keeping in mind, of course, that we're live streaming directly to YouTube. On
Oh,
the
excellent.
microphone right now.
Oops. No, it's great. It's great. It's fabulous. Let's see. Yeah, are you involved in like what is it? I feel like a bunch of folks in CFA were doing some like foreground, background, like kind of like stuff with like stars, like.
Yeah, Charlie Convoy's group is doing some of that. There's Jesse Hahn, who's a grad student, who's doing that.
I haven't kept up with that at all. Like,
yeah,
like
it's
what's
relatively new, I think.
Okay.
So no, I haven't really done a lot with that.
Yeah.
I'm mostly
Foggy.
Yeah, mostly.
I mean, Foggy is quite the project.
Working on 2.0.
Yeah.
Very exciting.
Yeah.
We're gonna have better simulations.
What's the specs on the upgrade?
Yeah,
Is it like resolution?
It's hopefully low resolution, but mostly just better physics. So we're hoping to improve the feedback scheme, which is my job. Our star formation scheme, get more realistic galaxies.
Shall we herd the flocks? So we start at that.
Well, it wasn't on, but hopefully I didn't break it. Yeah, no, that's a great idea.
The best way to get everybody.
Bit of a delay. Yeah, I try to avoid using laser pointers in general, so
It's convenient.
it's convenient for moving this. Right. Yeah.
But it's,
There's a huge delay.
nanosecond delay, which is just.
Love that ballad. Okay. Welcome to the final session of the day. In this session, we're going to cover the CGM, we're going to cover galaxy evolution, we're going to go from the Milky Way all the way out to highest redshifts. Before that, my name is Rohan Naidu. I'm a third year NASA Hubble Fellow at MIT, and I'm excited to be your afternoon entertainment chair. So starting us off is going to be Cassie Locus, who's going to tell us about galactic feedback and how it affects predictions for the CGM emission. Please take it away, Cassie.
Thank you. All right, thank you so much. So what I want to tell you about today is some predictions that I've been making using the foggy simulations with an eye towards the Aspera mission, that is an upcoming mission, to hopefully try to probe the circumgalactic medium in emission. But first, let's take a step back. The CGM, since we haven't heard any talks on this yet today, this is the region of space just outside of a galaxy, where all gas flows both in and out of the galaxy have to pass through this space. So you can imagine that it's quite important for regulating or even promoting the growth and evolution of galaxies. So historically, the way that we observe the CGM, because the gas is very diffuse, it's difficult to observe, is by looking for absorption towards bright background light sources. So if you have something like a distant quasar, as the light from that quasar travels through the CGM of some foreground galaxy, some of it is absorbed. And by looking at the ionization state of the elements that are absorbing, as well as their velocities, we can get some information on the kinematics, the densities, the temperatures of the gas in the CGM. So when you do these types of surveys, like the COS-HALO survey in 2011 here, you find a significant amount of one particular ion, oxygen-6. So this is a pretty highly ionized state of oxygen. And it's pretty much never the dominant ionization state of oxygen, but it has a very strong oscillator strength. So we can see it very strongly in absorption. So this plot that we're looking at here is the column density, there we go, column density of oxygen-6 as a function of distance out from the central galaxy. And each point on this plot is a single galaxy absorber system. So what we can see is that there's a good amount of oxygen-6 in the CGM of these are mostly Milky Way-like galaxies. But we don't really know what type of gas oxygen-6 is tracing. We don't know whether it's really warm or hot gas or sort of cooler gas. We don't know if it's located in the inflows or the outflows from this galaxy. So this is sort of an open question. And this is where Aspera comes in. So Aspera is a NASA Pioneer smallsat mission that is on schedule to be launched in 2025. The PI is Carlos Vargas at University of Arizona. And what it is a high sensitivity, wide field spectrograph that covers a very narrow wavelength range, just focusing on the oxygen-6 doublet. So the science goal here is to detect and hopefully spatially map oxygen-6 emission off the plane of edge-on galaxies. We're interested in the circumgalactic medium here, so we look at these galaxies edge-on to avoid confusion with the interstellar medium. So what I've been doing as a member of the science team for Aspera is using the foggy simulations to make some predictions for what we will hopefully see in terms of oxygen-6 emission. So foggy is cosmological simulations that zoom in on a handful of Milky Way-like galaxies. And in foggy, we force the CGM to be at a high resolution. So this will hopefully be good for being able to detect the sort of diffuse warm gas that we expect O6 to be coming from. These simulations are very computationally expensive already. I did not rerun them all with radiative transfer and non-equilibrium ionization chemistry, because that would have been even more expensive. So there are some caveats here. The way that the oxygen-6 is being calculated is sort of in post-processing from these simulations, where we just use the density and the temperature of the state of each resolution element in the simulation to infer what its oxygen-6 brightness would be. So the caveats here is that we don't have any sort of time evolution for those gas elements and how that might contribute to ionization. We kind of just have to assume ionization equilibrium. So with those caveats in mind, we are able to make oxygen-6 predictions. What we're looking at here is density of this edge-on galaxy on the left and oxygen-6 brightness on the right, evolving through time. There have been a whole bunch of papers on foggy on all sorts of various other topics. So if you're interested, feel free to take a look at those or ask me later. Okay, so let's look at what this map actually looks like. So this is one of our edge-on disk galaxies. So the disk is oriented sort of horizontally here, where we can see the sort of clumpy morphology of the bright oxygen-6 emission. If we look at this with an eye towards aspera, the slightly different color bar, where in this case, all of the gray is emission that is unfortunately below the detection limit for aspera. But we do still have some pretty clumpy morphology that's left pretty close to the galaxy here, where we do see bright oxygen-6 emission. So our sort of first prediction here is that at the low redshift, we're looking right at redshift 0 for this galaxy, the emission is bright and close to the galaxy disk and rather clumpy in morphology. And we do expect this clumpiness because emission scales as density squared. And in the CGM, usually the densest gas is in small clumps like this. So next we can ask the question of where is this oxygen-6 emitting gas actually located? So to do that, what we're looking at here is a surface brightness profile as a function of distance out from the galaxy, which would be down there at 0. The total profile is in black, and the shaded region there is showing both the time evolution and also the difference across 5 different galaxies from the foggy suite. And so right away we can tell if we break this up into inflowing gas in purple and the outflowing gas in orange, it's very clear that the inflowing gas dominates the oxygen-6 brightness. Of course, observations can't see inflowing versus outflowing gas, but we can try to estimate that by looking at perhaps along the major axis of the galaxy or along the minor axis of the galaxy, since sort of in our classical picture of galaxies, inflowing gas is perhaps coming in along the major axis and outflowing gas is coming in or coming out along the minor axis. So when we do that in the foggy simulations, we see that there's actually no difference in the surface brightness profile at all between the major and the minor axis. So this is interesting. This is telling us that even though this oxygen-6 is predominantly located in the inflowing gas, that inflowing gas is not actually coming in along the major axis. But if you remember, this O6 is in predominantly clumpy gas. So perhaps the clumpy inflow has a sort of different morphology than what we would expect from perhaps a smooth inflow that is coming in along the major axis. So this is maybe a little bit different than we might expect from sort of a classical picture of gas flows. And in fact, if we come back to the movies we're looking at here, you can kind of tell by eye in the emission moving on the right that a lot of the very bright material does appear to be sort of moving in towards the galaxy. It is located in the inflow. But you can't see too much sort of preferred direction except for very, very close to the galaxy disk where it does appear to be oriented sort of edge on. But most of the more widespread oxygen-6 emission is kind of just everywhere. So next we can ask the question of, does the O6 surface brightness correlate with any galaxy properties? So I looked at a number of different galaxy properties. The one that seems to have the strongest correlation is the star formation rate of that central galaxy. So what we're looking at here is, let's take a 20 kiloparsec in radius circle, plop it down on our galaxy. So we have a little cartoon in the upper corner here, more or less to scale if the inner sort of pink region is the stellar disk and that blue-yellow region is the extended gas disk. And if we just ask, what is the median oxygen-6 brightness within that circle, and plot that as a function of the central galaxy's star formation rate. So these different colors of these points here are the 5 different galaxies that we have in the foggy suite. They're all sort of roughly Milky Way-like by redshift 0. But then each different point on this plot is a single snapshot in time of that galaxy. So as these galaxies are evolving throughout time, they have different star formation rates. And that appears to correlate actually quite nicely with how much oxygen-6 emission we see in the CGM of these galaxies. And we can look at this a slightly different way by, instead of looking at the median brightness, let's look at the fraction of the area within that circle that is above the aspera detection limit. And we see that this also correlates quite well with the star formation rate of the central galaxy. So this is telling us that the oxygen-6 is sort of brighter and more widespread, at least in the central region close to the galaxy, when the star formation rate of that central galaxy is larger. But I just showed you that oxygen-6 is dominated by the inflows. We might expect that if this is correlated with star formation rate, maybe it's the outflows, since outflows are stronger when the star formation rate is higher. So instead we see perhaps this is an opposite correlation, where it's the inflowing material that is bright in oxygen-6, and that is maybe tracing the fuel for star formation and leading to those higher star formation rates. Now, we can test that explicitly in the simulations by simply turning off the outflows, turning off the stellar feedback. from that central galaxy. So if I do that, that's these orange points on these plots. And right away, you can tell that the oxygen-6 brightness and also its sort of spread within this inner region is much, much lower. So this is somewhat interesting because it's telling us that even though the oxygen-6 is located within the inflows predominantly, turning off the outflows from that galaxy also gets rid of a lot of oxygen-6 in the CGM. And in particular, if we look at this in movies as well, where we have the situation with outflows, with feedback on the left, and the situation without any outflows, no feedback on the right, you can very clearly tell by eye that while there is a good amount of oxygen-6 in the inflowing material, it's much more widespread when you have those outflows. So perhaps what's actually happening here is oxygen-6 is tracing some sort of interface or interaction between inflows and outflows. And even though it's predominantly in the inflowing gas, it is still very important to have those outflows in order to have that interaction. So what does all of this mean for Aspera? Well, we know that the emission is probably going to be, if it finds some, very close to the galaxy and will have a clumpy morphology as well. This also helps us determine our target list. So if more highly star-forming galaxies are brighter in oxygen-6, then we might want to try to target more highly star-forming galaxies in order to be able to detect this oxygen-6. And of course, once we can map the oxygen-6 in the circumgalactic medium with Aspera, perhaps those regions that are especially bright might be telling us something about where inflows and outflows are actually interacting with each other. So these are actually my conclusions, and I will leave it there and take questions. Thank you.
Questions for Cassie? Jay?
Thanks, super cool talk. Really cool simulations too. I guess I'm curious about how much of this is an enrichment problem. Because the oxygen has to get out into the CGM in the first place, so it totally makes sense that it's outflow effect.
Yes, yeah, that's a great question. So yeah, actually, so the question is this an enrichment problem? Is the reason why there's no O6 when we turn off the feedback, just there's no metals out there? That's a very good point. It very well could be that. The fact that there's still a good amount of O6, even in the inflowing gas, which is metal poor, especially when we turn off the feedback, makes me think that's probably not the entire story. But yes, I definitely think that will contribute.
Yeah.
I was curious if you looked into what fraction of oxygen-6 mass is in these photons as opposed to the diffuse or more diffuse gas that you wouldn't see.
Yeah, so the question is what fraction of mass is in the clumps versus in the more diffuse emission? I have not looked at that. That's a very good point. I would expect that by mass, there's probably more oxygen-6 in general in the diffuse material, just because I expect it to be tracing sort of warmer, more diffuse phases of gas. But it's just in the emission, it shows up in the denser material because of the density squared scaling.
One last question while Samskriti sets up, maybe. Ekta, I say.
I was wondering if you or the other collaborators have looked at this for slightly lower mass galaxies, or is there chances of doing it?
Yeah, so the question is, we looked at this for lower mass galaxies. So I have not looked at that myself, and unfortunately with Foggy, we don't have a whole lot of low mass galaxies, with the exception of whatever satellites of these Milky Way mass galaxies there are. So hopefully that's something we'll be able to do in the future, but no, I don't have an answer for you.
Well, thank you for all your questions, and let's thank Cassie for taking the up next, we have Sanskriti Das from Stanford University, who will be telling us about multi-wavelength observations of the hot CGM.
Thank you. Am I audible? Okay. So thanks to Cassie's talk, I mean, I don't really need to introduce what CGM is, so I kind of, removed some of the introductory slides. So hello, I'm Shamshriti. I'm a postdoc at Stanford University, and I work on both the hot CGM and cold CGM, but today I'm going to focus on the observations of hot CGM using X-ray and millimeters. So the CGM is obviously anything that's outside the stellar disk extending out to the virial radius, but when we say hot CGM, that primarily means anything that is highly ionized, and it has two components. One is the relatively low density metal core gas, that is coming from the intergalactic medium and is shock heated to the virial temperature that fills up the whole virial poly. But there is also gas which is relatively hotter, denser, and metal enriched that comes from both AGN and stellar feedback. And the mix of these two components decide what the detailed density, temperature, and metallicity profiles are going to be in the CGM. Now, the Milky Way CGM has been observed for last 30-ish years using both X-ray emission and absorption. And by combining those, we already know that Milky Way CGM is far extended out to its virial radius. It is very massive, massive enough to account for all the missing galactic variants in Milky Way CGM. So the next question is it Milky Way like special, or do we see the same thing for external galaxies? So I'll be talking about one project on detecting individual external galaxies using X-ray emission spectroscopy. And I'll also talk about the stacked galaxies in millimeter using Sunyaev-Zel'dovich effect. So I'll start with the CGM of individual external galaxies. And here the main challenge is to model the soft foreground, soft X-ray foreground, which accounts for almost 90 to 95% of the photons. So the signal detection is extremely sensitive to how we model the background, how we remove the background from the total data, and which part of the sky is chosen as the background. And also the target selection is extremely crucial. We have to be careful about the intrinsic properties of the galaxies, the environmental properties of the target, and as well as their 3D sky position. So here I'm going to focus on this one galaxy, NGC 3221. Its mass is roughly like Andromeda. It's highly star-forming galaxies, but not currently having any AGN. So we don't see any AGN feedback in the galaxy right now. And it's a free galaxy, so we do not confuse the CGM emission with any intra-group or intra-cluster media. And we analyze both XMM Newton and Suzaku data just to see if we find consistent emission in both the data sets. And also, as I said, the detection is extremely challenging to how we model the foreground. So instead of directly subtracting the background, we simultaneously model the background as well as the on-source data. So imagine having two equations, but having 7 unknowns. You cannot just solve that by subtracting one from the other. So you have to add a lot of additional conditions to remove the background from the total data. And here you can see all the different components together. This is the integrated emission from the whole CGM from 30 to 200 kiloparsec. And the main takeaway is that the total data is shown here in the gray circles. And the dashed line, which you can see here, is the soft X-ray background, which is the sum of all foregrounds and backgrounds. And this tiny excess here, coming from the oxygen 7 and 8 ions, are the actual signal from CGM, which accounts for only roughly 5% of the total data, which shows why it is extremely challenging to detect the emission. And we see it both in XMM Newton and Suzaku, showing that this is a consistent and robust result. And so far, it remains the first and only external spiral galaxy with this detection. One is probably not a large number, but still greater than 0. And we see some of the interesting properties. One is that the temperature is not constant across the whole CGM. It increases, becomes supervirial inside 100 kiloparsec. And also within 100 kiloparsec, the surface brightness is not constant. In fact, across the minor axis, we see that the surface brightness is roughly 2 sigma smaller than the global average. And if we combine these two results, it indicates that the stellar feedback might be pushing out the pre-existing CGM, thus creating a cavity and also dumping the thermal energy. Also, here is the emission profile, emission measure profile, which is basically the integration of density square along the line of sight. And we model it with the beta profile, where we find that the core radius is actually almost as large as 60% of the virial radius, showing that the CGM profile is extremely flat. So you need to probe out to a large radius to really figure out whether it's a CGM or you're seeing a flat field of the background. And the baryon fraction is actually quite uncertain because of the large error bar, which you can probably guess from the quality of the data. But now we are working on a 10 times deeper data set from XMM Newton. We hope to get a more precise measurement from this. Now moving on to the millimeter measurements. So here we use the Sunai-Zeldovich effect, which is basically the inverse Compton scattering of the CMB photons with any intervening ionized medium. So CGM, here the thermal SG effect gives us the measure of thermal pressure or the integrated thermal energy of the CGM. And this has been traditionally used to measure the thermal pressure of galaxy clusters, where individual clusters are detectable. But here we cannot detect the signal from individual galaxies. So what we have to do is cross-correlate galaxy catalogs with CMB footprints and stack over hundreds of thousands of galaxies to be able to reduce the statistical noise and be able to separate out the detection from the CGM from all the other 0-point offsets and the 2 helitards. So here we have used the WISE and Supercosmos Galaxy Catalog. Here you can see the relation between stellar mass and redshift, where we focus roughly on 10 to the power 9.8 to 11.3 solar mass galaxies. Previously, the focus was mostly on low mass galaxy groups or individual galaxies more massive than these. And also, since the interpretation of stacking results are always really hard, we focus on galaxies which are not inside galaxy groups or galaxy clusters, so that we can separate out the individual signal from the CGM. And also we exclude radio galaxies or galaxies that might potentially have AGN, because if the AGN has wind, it will have a positive effect on the AZ effect. But if the AGN has jet, it might actually have a negative effect because it might eject the existing gas outside the virial radius. And if you're stacking thousands of galaxies, you never know what fraction of AGNs are affecting positively or negatively your signal detection. So this just makes our interpretation much easier. And also in the CMB side, we use the Atacama Cosmology Telescope's, I think, data release 4. And we have only used the subset of the footprint, where we also have the DAISY group catalog, so that we can cross-correlate the galaxy catalog with the group catalog and remove the galaxies which are parts of galaxy group, so that we can focus only on the field galaxies. Now, by cross-correlating the galaxies with the CMB footprint, we find the stack map looking something like this. So here on the right-hand side, you can see the stacked map, where the blue part is basically the positive Compton Y, and this roughly blue blob is an indirect detection of the CGM. But this has 3 different components. So one is the 1 kiloton, which is the actual CGM signal. And also we have the 2 kiloton, which is basically all the other galaxies which are around the galaxy not being stacked, but their additional component can actually add a almost flat looking signal. And also because of the calibration uncertainty, we add a 0-point offset. So this green line corresponds to all the backgrounds. And the fact that these black points are in excess compared to the green is the detection of the SZ signal. Then we repeat this for the all mass beams we have considered and calculate the thermal energy and the baryon fraction for all the mass beams. So here on the left, you can see the thermal energy, and right is the baryon fraction. For the thermal energy, if there is no effect of the feedback, we expect the galaxies to be baryon sufficient and just follow the simple self-similar relation that we see for galaxy clusters. But as you can see here, our best fit is significantly steeper than the self-similar relation, which shows that the effect of feedback is much stronger than the self-similar effect. But also we know that for individual more massive galaxies and for low mass galaxy groups, they fall somewhere around here. So if you just extrapolate the effect of more massive galaxies here, we expect something like this. But we find that the galaxies actually have more thermal energy than we expect just by extrapolating for more massive galaxies. Now, the interesting thing here is that slightly above this halo mass, we expect the AGN feedback to be more dominant. And as we go to lower and lower mass, we expect the stellar feedback to be more dominant. So we are actually exploring the sweet spot where the most dominant feedback translates from AGN to stellar feedback, and that is why we are seeing this deviation in terms of both slope and normalization. And you can see that also for the baryon fraction, where we see that baryon fraction actually increases with decreasing mass. It becomes baryon sufficient at a certain point. And coincidentally, the individual galaxy we observed also happens to be here. It is totally by chance. We didn't plan this way. And also we can see that here the baryon fraction again decreases with mass. Now the fact that we see this inverse relation has also been predicted in simulations, not exactly at this mass, but this is interpreted as the dominant feedback mechanism changes from AGN feedback to stellar feedback. And to understand this effect of feedback better, we are now studying the DAISY galaxies, again stacking and cross-correlating over CMB footprint with the DAISY galaxies, but now splitting between star-forming and quiescent galaxies. And here you can clearly see that the star-forming galaxies look significantly different from quiescent galaxies. So the star-forming galaxies have this bright blob indicating that they might have a stronger SZ effect / thermal energy than the quiescent galaxies. But this is before removing the two halo terms, so take it with a pinch of salt. So having said that, I will leave with my summary. The main point is that detecting individual galaxies and stacked galaxies are both important because we need to know how the detailed density and temperature profile looks like in individual galaxies, and also know how overall hundreds of thousands of galaxies look like. But also, since density emission is density squared, it is dominated by the inner CGM, while SZ effect probes the more extended low density medium. We need to study both individual and stacked galaxies and both X-ray and SZ galaxies. And I will just end up by saying that next generation millimeter and X-ray telescopes will definitely be better, but we should also fully utilize the capability of existing telescopes and especially the X-ray telescopes so that we can distinguish between different CGM models that conflict because of the feedback prescriptions. So having said that, I'd stop and take questions.
Questions, Michael?
Thank you, that was interesting. I was wondering when you're talking about the individual galaxy and TP-3021, so you chose that the galaxy has, you said has an AGN, right? When you're showing the azimuthal surface price profile, you showed there's heavens and cavities, so presumably that's not from AGN. So do you expect that's probably like stellar, like winds from star formation or something like that? Or where the cavities come from?
Yeah, that's a good question. So the question is that if I can go back. So the surface brightness profile actually has this cavity along the minor axis. And this could be because of any centrally driven outflow because of AGN or the star formation feedback. And since currently the star formation rate of this galaxy is 10 solar mass per year, we cannot rule out the possibility of stellar feedback creating this. And we do not have any evidence of past AGN feedback from any other wavelengths. So it is not impossible that the cavity is created by past AGN feedbacks, but just from this surface brightness, we cannot figure out the possibilities. Now, with the new data, we are planning to do more detailed analysis to figure out the size of the cavity, where we can do this same analysis of different, radial extents. This is only for within 100 kiloparsec. And from the size, we can roughly estimate the power inserted, which is larger for AGN. And there we might be able to distinguish, but that's, part of the plan.
One last question while Sadie sets up. Yeah.
Super cool talk. Have you tried stacking subsets of the data that went into what you used it? Like inevitably you get the SC detection. I'm curious about like the mass completeness of that range of your reports. It kind of makes me have a lot of those. The detection is super cool on the left. I'm wondering if maybe you could kind of reproduce that with a more mass event, or if you want to get a sensitive at those numbers to like be able to stack down the low mass halos and recover signal there.
Yeah, so if I understand your question correctly, if I have tried stacking for subsets of the total sample. So we just tried splitting it into two subsets because we didn't have a lot of galaxies in every mass being to try it. So actually the error bar is too large when we split it into two subsets, and they are consistent within error. But with the DAISY galaxies, we have 10 times larger samples. So there we plan to split it again and figure out if that is creating some systematics.
Let's hear it again for some. Up next, we are going to go to the very high redshift universe and hear from Seiji Fujimoto, who is going to tell us about what I find me is one of the most stunning galaxies we've observed in university yet. We're going to see a primordial rotating disk composed of greater than 15 dense star-forming clumps of cosmic dawn.
Okay.
Take it away, Seiji.
Okay, thank you. Okay, hello everyone. My name is Seiji Fujimoto, currently working at UD Austin as a Hubble Fellow. So this is my final year, so it's a little pity, but yeah, it's always a great pleasure for me to come here to see new faces and some of the old friendly faces here and there. So yeah, today I will talk about some of the exciting outcomes from the latest JWST and ALMA observation for the high-edge galaxy. But yeah, one of the key takeaway message is what I bring here today is one of the deepest image, beautiful image of the early galaxy. So even if you are not familiar with the high-edge galaxy stuff, I hope you like it. So and also I'd like to share some of the my update about myself. So yeah, fortunately, thanks to the very great excitement in the last few years, I recently got the offer from the University of Toronto. So I will join in faculty from next summer. So this is all thanks to the great opportunity enabled by Hubble Fellows this program and great colleague like you all. So I really looking forward to keep this academic journey with you all. Okay, so first of all, why we have to care about the high-edge universe? Well, in my understanding, I believe the first something always has the largest influence on how the things go afterwards. So the similar thing also happens in the universe. So this kind of high-edge universe and early galaxy always tightly related to the fundamental question like development of the large-scale structure, process of the cosmic ionization, and emergence of the first galaxy and black hole. So we, extragalactic astronomer, always has a very big passion to explore the very distant universe. And in this context, a few years ago, JWST gave us a very revolutionary opportunity to discover more, explore the distant universe, and we very surprised to see the remarkable high abundance of very bright massive galaxy. So here actually highlight two very uniquely bright galaxy, even redshift beyond 10, actually discovered by Rohan here. So yeah, NASA press release also published like this. And afterwards, some independent team also systematically searched similarly bright objects by using all public data of JWST at that time. And they also confirmed that this large abundance, so the abundance seems to be higher than all simulation prediction made before JWST. And here, some of the systematic spectroscopic follow-up efforts have been also made. So the right panel shows the UV luminosity function, so the abundance of the galaxy as a function of the absolute UV magnitude. So this kind of multi-object spectroscopy in the mask design, we cannot include all photometric candidates. So here, what we can provide is on still lower limit, but still this lower boundary already starts to deviate from the many simulation prediction showing this dashed color line. So now this kind of high remarkable abundance of very bright galaxies seem to be real, spectroscopically confirmed. So the next question is, what is the physical mechanism which makes this overabundance? And in the last few years, many intensive discussions have been made. Maybe in the very high redshift universe, initial mass function could be more top heavy, or AGN could be also more abundant, and their UV luminosity contribute to this total luminosity, or star formation efficiency somehow high, or vast star formation stochasticity skew the bright end of the UV luminosity function shape. So these are many possible scenarios have been argued. To tackle this question, I believe one important approach would be resolving the galaxy structure, because all relevant physics, so star formation or emergence of agent, are taking place inside of the galaxy. But the difficulty in this kind of high-resolution galaxy study is that not only the sensitivity, but also the spatial resolution. So what we usually get is like this. So it's almost impossible to get inside of the galaxy. But to overcome these two approaches, one plausible idea approach would be maximum usage of the gravitational lensing. So not only the flux boosting, but also the structure is nicely magnified, stretched out, so we can easily get inside of the galaxy, and we can study what's going on in there.
So in this context, I'd like to introduce this intensive follow-up campaign just for a single lens galaxy at redshift 6. So one of the highlights here is a total of 160 hours of JWC and ALMA and Muse time has been invested just for single galaxy. So that's why at the beginning I told you that I can bring you one of the deepest, most beautiful image from the one of the high redshift galaxy. So yeah, the target is very uniquely lens multiple lens galaxy discovered behind one of the massive lensing cluster. And yeah, here the zooming panel showed all multiple images already spectroscopically confirmed at the same redshift 6. So the biggest advantage of this system is that these two brightest multiple images, thanks to the high magnification, the observed flags is known to be one of the brightest objects so far spectroscopically confirmed at redshift beyond 6. But thanks to the lensing, after lensing correction, they are still intrinsically very faint. So the surface low mass main sequence galaxy. So yeah, even comparable to the local dwarf galaxy. So although thanks to the brightness, we can save the observation time a lot, but still we can understand what the typical. So yeah, this still represents typical galaxy, very abundant galaxy. So this is very unique laboratory what's going on in the early universe, early galaxy. So yeah, I'd like to in the remaining minutes, I'd like to show some of the exciting highlights from this intensive follow-up campaign. So first, morphology. So the galaxy. So this is how one of the multiple image look like before JWST. So this is the foreground object, and this is our target. So from HST, the galaxy looks like a very smooth disk-like galaxy, and the size is effective radius 700 parsec. When we apply the cell-stick profile fitting, it shows exponential disk profile. Okay, so this is very typical disk-like galaxy. But now we have a near-term JWST data, 3 times better spatial resolution. The galaxy look like this. So the single disk-like galaxy is resolved into at least 15 individual star forming clumps, and after lensing correction, this individual clumps is now 10 to 60 parsec scale, but still dominating the 70% of the total flux of the system. So this is totally different from how the general disk galaxy in the local universe look like. So this clearly tells that this early galaxy is different, not just a smaller scale of the local disk galaxy. And yeah, this is literally changing our view how the early galaxy look like. So yeah, from this morphology, we named this object here, the cosmic rays. I hope this makes sense. Yeah. So we are so impressed by this morphology. So we also did some dedicated morphological study for this cosmic ray. So here shows the source plane reconstructed image. So now the morphology a little flipped. But yeah, now thanks to the high resolution near-term and also supported by lensing effect, the effective resolution scale is now achieved down to 0.1 arcsecond scale. But if we don't have the lensing support, okay, here we apply the smoothing to downgrade the spatial resolution to match the nominal near-term resolution. The galaxy morphology look like very single smooth disk-like galaxy. So this caused us, gave us a very important notion here. So here actually highlights some of the high redshift galaxy candidate identified the recent JWST near-term data. And actually, these galaxies always look like very single disk-like galaxy. But in reality, here we have the true picture, 5 times better resolution. This single disk-like galaxy resolved into numerous counts. Although this is still only for one example, but you remember that this represents the main typical low mass galaxy. So this could be the case in many also other JWST single disk-like galaxy. But of course, if the galaxy morphology look like this, some of you may wonder that this could be just complicated merger system. So the great advantage of this here is that we also have the very deep IFU data, so we can study the gas kinematics. And here we show the cold gas dynamics obtained by ALMA, so the moment 0, 1, 2 map, and also ionized gas kinematics taken from JWST near spec IFU. So both C plus and H alpha ionized gas nicely show the smooth velocity gradient, symmetric feature. So when we apply the dedicated kinematic modeling, it suggests that this is a nicely rotation supported system rather than a complicated merger system. And also we got a very smooth, here show the radial, so the rotation velocity and velocity dispersion. And we find that somehow the ionized gas show higher velocity dispersion, but this is from simulation prediction. This is explained by simply by the ionized gas is always more easier to be influenced by feedback effect. So this makes this a little difference. But this also suggests that C plus gas nicely trace a cold, smooth underlying ISM gas from the system. Then V over sigma seem to see, so it's nicely rotation supported system. So now from this very high resolution deep data, we start to understand that okay, early galaxies seem to be consist of numerous clumps embedded in the smooth rotating disk. But we soon realized that this is very challenging to the current early galaxy formation simulation models. So the thing is that here I highlight two simulated galaxies. So in one case, okay, we can see that very smooth rotating disk reproduced, but the number of clumps is not that much. And the other case at the bottom line, bottom long line. So we could identify more numerous clump, but in this case, this kind of numerous clump was formed through the more vastly star formation history, then more strong feedback effect subsequently emerged, then the underlying smooth disk is easily blown away. Then it's really hard to maintain smooth rotating disk like this. So having both numerous clumps which require very frequent vastness and also smooth rotating disk is really conflicting each other. To reconcile these two situations, one possible plausible scenario is the feedback effect in this early galaxy is very weak. Actually, this could be not that bad idea because high latitude galaxy is getting very compact, then gas density getting high, then the self shielding effect happens, then feedback effect can be weak. And actually, in the last slide, I'd like to show that we actually confirmed such a high gas density and weak feedback effect in this system. So C++, as I mentioned, I have nicely tracing the cold smooth gas. So it also often used as a molecular gas mass proof estimator. So based on empirical calculation, we also cross-check with the dynamical mass estimate, also armed with some metallicity measurement. Then we can derive the spatially resolved star formation rate as a function of the spatially resolved gas mass density, so-called Kennicutt-Schmidt relation. So from the entire galaxy scale and spatially resolved individual clump scale shown in this red symbol. Then we find that our galaxy from entire to the spatial resolved scale are nicely consistent with the local Kennicutt-Schmidt relation. But more excitingly, in this spatially resolved measurement, some of the bright clumps show the very high gas density, which even more than 10 to 3 or 10 to 4. And right panel shows the star formation efficiency as a function of the molecular gas density estimate predicted in the radiative hydrodynamic simulation, including this feedback effect. So again, as I mentioned, if the gas density is high, the molecular clouds having the start to have more strong self-shielding effect, then star formation efficiency can be naturally high. Here I'm using the word star formation efficiency word as a time average number. Then it can be very high, almost close to 1. So this is actually a very huge contrast from the local galaxy. And so the you may remember that I mentioned some of the possible scenario which makes early galaxy remarkable high abundance of the early galaxy. So based on this result, so the high star formation efficiency scenario could be one most plausible scenario among them. Okay, so here's a summary. So we start to see the spectroscopically confirm this kind of remarkable overabundance of the early galaxy. And we have achieved very high resolution observation. Then early galaxies seem to be consist of the numerous clumps embedded in smooth rotating disks, which require a very weak feedback effect, which might be the reason why we start to see such a high abundance of the remarkable bright galaxy in the early universe. Okay, thank you and happy birthday.
We have time for 2 quick questions. Let's go. Karthik.
Really cool stuff as always.
Thank you.
there is evidence from simulations like Venkatathan that show that like early systems that are more gas rich tend to be more clumpy. Do you find anything like that in the system?
So the question is that, yeah, so some of the simulation actually predicts such high gas densities, and the clumpy structure is naturally predicted. We check all several famous represented early galaxy simulation, but actually this high gas density, so the observation we got 70 or 80% high gas fraction, but yeah, simulation still predict get 50% of that kind of number. So actually, we discussed that still simulation might still need more high gas density to reproduce this kind of clumpy structure. Yeah.
One last question while Adam gets ready. Go ahead.
Is that a physical size of the galaxy? And if that's the case, all galaxies are diverging in function, that's tiny.
Sorry, so your question is the entire galaxy size, and so the entire galaxy's size, effective radius is 700 parsec scale, and individual clumps is 10 to 50 parsec scale.
Wow, okay.
Yeah, at redshift 6, thanks to the gravitational lensing effect. Yeah.
So let's thank Seiji again.
Yeah, thank you.
Thank you so much. Next up, perhaps at more familiar scales in the Milky Way, we'll hear from Alex Messina, who's going to tell us about a new portrait of the triangular galaxy. Take it away, Adam. Here you go.
Thanks a lot. So yeah, I'm Adam Smersina. I'm a new Hubble Fellow at the Space Telescope Science Institute. And I'm going to talk to you about some of the work I've been doing over the past couple of years into the next few years on resolved star studies in nearby galaxies. And this is going to be pitched as a galaxy evolution talk. So I'm going to start with a simulation. This is showing a galaxy in TNG 50 that is going to end up being very similar to our own Milky Way by the end of the simulation. And you can see, oh, this is weird. You can see throughout the lifetime of this galaxy, it's experiencing a lot of these different kind of mergers and accretions. You can see it in the gas in the center here, in the dark matter, and in the stars on the bottom right. And as it's experiencing these things, you can see the star formation rate changing, and also the structure of the galaxy changing as it experiences these events, right? And so this is galaxy evolution in action, and this is what I'm really interested in, right? How these kinds of merger events that galaxies experience, how they influence these kind of present day properties that we see, and how it results in the evolutionary history of galaxies that we can measure. But the gas here, this brilliant picture of the gas, we can't see this, right? After a couple of dynamical times, you lose almost all of this information. And so you need longer lived tracers of the long-term evolution of a galaxy, and this is the stars, right? And so we have studied the global stellar populations of the Milky Way, of course. We know a lot about the evolutionary history of the Milky Way, of Andromeda, of the Magellanic Clouds. And the last kind of big important member of our local group of galaxies that there's still some mystery surrounding its evolution is M33, the Triangulum Galaxy. And M33 is kind of this prototypical late type spiral galaxy. It's got this very beautiful flocculent spiral structure. And over the last few years, we have used HST data as part of this FATTER survey to survey a substantial fraction of the disk of M33 in a number of different filters from the UV to infrared. And we've resolved 22 million individual stars in this galaxy. And so, this beautiful optical image on the right or on the left here, there are, 22 million stars that you can pull out of this galaxy. You can kind of see the graininess of the image here. And what that translates to quantitatively, the type of information that we can extract, is something like this color magnitude diagram that you see off to the right here. And I have labeled a number of important features of stellar evolution that you can kind of pick out by eye if you know what you're looking at. And you know, some of the important ones here, we have the upper main sequence. These are our young luminous main sequence stars. We have things post main sequence, massive stars such as the core helium burners here. Of course, the red giant branch, and really important ancient age indicators such as the red clump feature shown at the bottom here. And to give you a sense of what we can do with a global survey of the stellar populations of a galaxy like this, you can really learn some new, exciting, unexpected things. Even a galaxy that is as well known as M33, there were some surprises here. So looking to the left here, this is the image, the mosaic image from Fatter again. If I plot over the same scale, the spatial density of now the upper main sequence stars, so these are the youngest, most luminous stars in M33, you can see that this flocculent spiral structure really just pops out, right? This is kind of what your eye is drawn to in a lot of images of M33. When we switch to the slightly older, still pretty young, couple 100 million year old, on average, core helium burning stars, things look pretty similar. They're starting to change a little bit. You can start to see some structure in the center of the galaxy, this kind of barish structure. I'm giving it away a little bit, but that is not really that apparent in either the image or in the main sequence stars. And if we go to now the most ancient populations, these RGB stars, red giant branch stars, are tracing the bulk of the stellar mass in M33. The structure is now completely different, right? From both this image over here, as well as the kind of main sequence stars in the first density map, right? So the primary structure of M33, traced by the bulk of its stellar mass at least, is a two-arm barred spiral galaxy. And this is something that we really did not have access to until we were able to resolve its global stellar populations. And it has some interesting implications that I'm not going to get into for the evolution of kind of low mass spiral galaxies like M33. Of course, another piece of this that we're really interested in is the star formation history of galaxies like M33. And this goes back to the simulation I was showing in the first slide. Obviously, these kind of mergers that galaxies experience have an impact on the star formation rate of galaxies over time. We're really interested in learning, you know, how this affects, you know, galaxies that we have access to in the nearby universe. What I'm going to talk about here is, you know, over much of this field, we do have access to kind of the full stellar populations where we could calculate an ancient star formation history back to many billions of years ago from M33. But the central region where there's so many interesting things happening, the bar, the pileup of accreted debris potentially from these kinds of past mergers. It turns out that we're kind of hitting, even with HST, we're hitting a kind of fundamental limitation in the crowding of stellar sources, right? And so with the crowding limit, it doesn't matter if you integrate for longer, you're not going to get any deeper in your kind of resolved photometry. And so this crowding limit for this kind of central region of M33 is right about here, this line I've drawn. And so, you know, this is about as deep as we can get for the center of the galaxy, unfortunately, which of course we miss some of these really informative features such as the red clump and the lower main sequence. So we have this other telescope now in the sky, right? And, you know, it turns out that JWST is a bit higher resolution than Hubble and has been able, and that has translated to a substantial improvement in our ability to do the science. So I'm going to show you what that looks like here. So I'm going to zoom in on this central region of the fatter image here. So this is what we see with HST, which is of course lovely. And this is the corresponding image that you get from our NearCam observations with JWST. This is from a cycle 1 proposal. And, you know, overall, this image is just absolutely beautiful, right? So I'm going to zoom in. I love zooming in on this giant star forming region, NGC 595. You can literally see the young stellar cluster here, the cluster of young stars blowing bubbles into the surrounding ISM, just excavating the ISM around it. And this is, kind of the expectation of the quality of data that we have come to expect from JWST. But more relevant to this talk is that what you can also see is stars all the way down to the center of the galaxy, even down to the scale of the nuclear star cluster in the center of M33. And we can see, down to very deep photometric limits. And so I want to give you a quantitative comparison of what this looks like. This is the color magnitude diagram from FATTR in the very center of the galaxy. And on the right is the color magnitude diagram from NIRCam over the exact same area. And you can, I hope, immediately see that the one on the right is deeper, right? Especially because we can see this very information-rich red clump feature that's completely resolved, right? And look at the exposure time difference, right? This is what you get when you're not crowding limited. And so we just have this beautiful data where we do now have access to the ancient star formation history. So this slide is now very preliminary work, and I just want to share. So this is the central shortwave NIRCam detector, and that 3-color image. So it's about 230 parsecs on a side or so. You can see the very center of the galaxy up here in the left corner. And if we take the stars that we detect in this image and fit for the star formation history going back the entire lifetime of the galaxy, you get something that looks like this. So the cumulative star formation history along the y-axis goes from 0 to 100% of the present day solar mass. Bear in mind that things at the most ancient time bins are pretty uncertain because we don't reach the old main sequence turnoff. But everything from about 8 billion years to the present day is fair game. And you can see that there really wasn't much happening from 8 billion years until a few billion years ago in the center of M33. And then it just sort of lit up, right? 40% of the stellar mass in this field was formed in the last 2 billion years. And we really don't understand why yet, right? So what happened in the center of M33? I'm going to leave that as a kind of an open question, something that I'm going to be investigating over the next couple of years, but it's really interesting. And so the last thing I want to talk about very quickly is using, translating this progress we've made with JWST and its improved resolution in advancing these kinds of resolved star studies further out into the nearby universe to some other galaxies that really highlight fundamental processes of galaxy evolution that we've not yet had access to. And I want to talk about M82 here. So M82 is I would say, the prototypical massive starburst galaxy. Most of us are familiar with this beautiful image from HST that's been around for 20 years now. And we got 66 hours of NIRCam imaging approved last cycle to cover this kind of white rectangular region here, the entire disk of M82. And we're expecting to detect somewhere between 20 and 30 million stars across the disk. And I want to show you a little bit about what that looks like in improvement over HST. This is kind of the typical CMD that you would recover from the main part of the disk of M82. It's very extinguished by dust. It's and reddened by dust. It's very crowded. And this is the typical CMD that we're expecting to recover with the NIRCam imaging over 85–90% of the disk of M82. Even if we go more towards the center, the midplane of the disk, where things are much more crowded, much dustier, we're still going to be able to resolve this information-rich red clump feature. And so we're going to have access over basically the entire disk of M82, this beautiful starburst galaxy. We're going to understand at an intimate level the evolutionary history of this galaxy. So to summarize, these resolved star surveys do reveal the evolutionary histories of galaxies. We found some really surprising and interesting things in M33 regarding, kind of hidden structure that was not apparent in traditional imaging. JWST's improved resolution has helped us reveal the crowded center of M33, and we're learning some very interesting things about its star formation history. and more soon. And then leveraging this improvement in resolution with JWST, we're able to now advance into the nearby universe. And I'm going to be conducting this study, this global survey of the M82 galaxy with NearCam. Those data are gonna come sometime early next year. So stay tuned.
Questions for Adam?
So you've got, what, 4 filters total?
Yeah.
So can you use that data to sort of de-redden individual stars based on what kinds of stars are allowed in the universe, and then tighten up the CMDs?
Absolutely. That's work that we are engaged in as part of the FATR survey. The FAT program kind of did some of this beforehand. Multi-filter photometry definitely helps you de-redden the CMD, especially when you have the near infrared bands. So you have to have a good model of what the dust distribution is doing, right? So that's the hard part, is trying to understand how the dust is distributed, especially in an edge-on galaxy, for example. But in M33, things are a little bit easier because it's face-on, right? And so, that's kind of work in progress. But yeah, the multi-filter photometry definitely helps you. Yeah.
Yes.
So an obvious candidate for that would be a satellite, right?
Yes.
So would your data already have revealed that the satellite was the answer, or?
It's a good question. You're talking about M33, for example? Yeah.
I'll turn it around.
Well, so I'm going to defer a little bit to Actus talk right after mine. I think she'll have some information about this. I think that in a recent accretion of a satellite from M33, we don't see any tidal streams around M33, right? And there's the PANDAS data set, for example, ground-based resolve star survey doesn't reveal any low surface brightness kind of stream structures. There is a warp in the outer parts of M33. And so something happened. My guess is that I'm going to go out on a limb and say that whatever happened in the middle is related to whatever caused this warp in the outer parts. I'm not going to go out too far on that limb and say what that might be, but I think they're probably related. Yeah.
Great. One last question from GI, who's been raising his hand for quite a while, and maybe I can set up while you ask and discuss.
So thinking about this kind of result, star population studies, how far in distance can we push?
With JWST, it depends on the galaxy we're looking at. For an edge-on high surface brightness galaxy like M82, this might be it, right? So this, we might have just gone to the edge of what we're able to do. I think, if we're talking about the outer parts of galaxies, the outer parts of disks and things, we might be able to push out to 10 megaparsecs or something, which is really exciting because if you think about that, all the different types of galaxies that are out at 10 megaparsecs that we don't have in the immediate, couple megaparsecs around the Milky Way, there's a lot of interesting processes shaping galaxy evolution that we see in galaxies that, in that volume, right? And so, yeah, it's going to be interesting to see what we can do.
Let's hear it again for Adam.
What's the deal with this?
And for our last talk of the day, we have Ekta Patel from the University of Utah, who will be telling us about the dynamics of the very fascinating systems we just saw a completely different view of. Take it away.
Thanks, Roman. Hi, everyone. We've made it to the end of the first day. Thanks for keeping your attention for 15 more minutes. So today I'll be talking about preliminary work. So feedback is definitely welcome. And it's preliminary, it's fresh from working with a summer student, Taj Noland, at the University of Utah. So it's Taj's first research project, and he's got some awesome results. So I'm excited to share this with you all today. So as mentioned, I'll be talking about the dynamics of the Andromeda, Triangulum, and M32 system, or in short, M32 plus or minus 1. But Todd Lauer already beat me to this paper title in 1998, so I can't use it. But that's what we'll be talking about today. But before we get there, let's just look at how we can compare Andromeda and the Milky Way and some of the similarities and differences that we see. So in this illustration, at least at face value, you probably think that these galaxies look quite similar to each other, which is a very fair assumption to make. We see lots of satellite galaxies around both the Milky Way and Andromeda. They're both barred spirals. They have similar rotation periods. They both host a massive satellite galaxy, the LMC in the Milky Way, M33 or Triangulum around Andromeda. And we see all of these beautiful stellar streams that show us that there have been many disrupted satellite galaxies and globular clusters around both of these massive galaxies. But what this image doesn't show you just yet is that what we've been learning, especially in the recent decade or two, is that the accretion history of the Andromeda galaxy appears to be a lot more complex, at least in the recent history, compared to that of the Milky Way. So while the Milky Way has had many mergers, we think 10 billion years ago, and then some minor mergers more recently, we think Andromeda has been having a lot more activity in just the last few billion years. So let's look at some real data of the Andromeda galaxy. So this is a stellar density map from the Pan-Andromeda Archaeological Survey. Adam mentioned this as well. So this is the widest, deepest survey to date of the Andromeda galaxy. And this larger circle goes out to about 150 kiloparsecs, or roughly half the real radius of M31. And of course, where you see the darkest points, you're looking at the highest stellar density. Now, the reason why we think that there's been a much more active recent accretion history, I'll give you one example of that, is because we can start to use models and simulations to link some of these events together and give a timing to them. So one of those such things is we see that there's this giant southern stream, which I've outlined in this white contour. So this is a very large stellar stream extending to about 100 kiloparsecs in projection. And models have claimed that this giant southern stream is linked to this eastern shelf, which is a clump of stars, and a western shelf, another clump of stars, that may have been linked all to the same satellite galaxy being torn apart by M31 and leaving behind these stellar remnants. However, what's not clear yet is whether this was caused by a minor merger or a major merger with Andromeda. So there's lots of questions still remaining to be answered, and hopefully we'll get a little bit closer to this. In addition to that, as Adam nicely introduced, we have, of course, Triangulum or M33, which is about 10% the mass of M31. As you can see in this image, it's very large in physical extent, and it's also very massive compared to its host galaxy. It is very similar to the Large Magellanic Cloud in terms of its halo mass, so it's about 10 to the 11 solar masses. So it already poses an interesting question of, is there any relation between M33 and M31, especially with regards to whether they've interacted in the past? If we zoom in to M31's disk, we also see some interesting structures. So there's a zoomed in image of the disk, and if you look at it in the infrared, this is an image from Herschel, you see it light up. And what you're looking at are primarily is a 10 kiloparsec star forming ring. There's many theories about how that has formed. I'll tell you about a couple of them in a few minutes. And we also know that there's been increased star formation activity about 2 to 4 billion years ago across Andromeda as well. In addition to that, I'll introduce the third galaxy I'll talk about, which is M32. So M32 is this compact dwarf galaxy, and we think it lies in front of M31's disk. So these are essentially the three main players that I'll be talking about for the rest of today. Until now, many studies have looked at these accretion events and tried to understand exactly what's happened to get to the properties that we observe today, one at a time. So we look at one stellar stream or one disrupted globular cluster, and we try to understand what was the evolutionary history of that particular object. But of course, we want to understand what is the global accretion history of the system, and how are all of these different major galaxies orbiting around Andromeda also interacting with each other. So before I get to that, I just want to introduce a couple of the theories that exist in the literature, since they'll be relevant for some of our results. So if we look at theories for how the giant southern stream, that very prominent stream of stars, formed, there's a couple of different paradigms. So one is that there was a minor merger, where there was a spiral galaxy, maybe 1 to 10 mass ratio with M31. It spiraled in, and it was torn completely apart, leaving behind that giant southern stream and some of the other stellar structures I was pointing out earlier. Similarly, there's also theories that there could have been a major merger, so a more massive galaxy that resulted in the same remnant stellar features. Another theory, which is illustrated in this figure here, is that that major merger was with a galaxy that is referred to as M32P, which we observe as M32 at present day, meaning that M32 is thought to have been much more massive in the past, and perhaps maybe even a disk galaxy that's lost a lot of its stars in the outskirts, and we're essentially left with just this nucleated core of stars, and that's why we observe it as this very compact object now. If we look at other ideas about what might have happened to M32, also minor merger is a possibility. So it could have just been a minor galaxy that was stripped of its outer stars and left with this nucleated core. There's also a possibility that M32 collided with M31's disk in the past, and that is what caused that star-forming ring that I was showing in the infrared image. And then finally, of course, the major merger scenario where M32P is the progenitor, which links together both the formation of the giant southern stream and how we observe the properties of M32 today. So let's move on to talking about what we can do with current data and moving towards a more holistic picture of how not just these two features, but also M33 are all dynamically interacting together. So this left image is a nice image from Adam, actually, showing M33 again. And the contours are highlighting actually not only just stellar debris or warps in the outskirts of the stellar disk of M33, which is in the red contours, but also a warp in the H1 disk around M33. And to give you a little bit of background, when the PANDA survey came out and many of the results were published back in 2009, of course, there was an interesting question of, well, how did M33 arrive at the morphology that we observe today? And as many theorists do, they ran a bunch of simulations to try to understand in an n-body setup, how do you get, what kind of orbit best reproduces this observed morphology? And the answer to that, specifically to reproduce the stellar warps, was a scenario where M33 and M31 had a recent tidal encounter with each other. Fast forward a little bit to actually having measurements for the 3D space motions of both M33 and M31. Early in graduate school, I showed that if you ask the question which orbital histories are allowed within the measured 60 phase space, rather than what reproduces the morphology, you get a couple of different orbital scenarios. And statistically speaking, at least within the measurement uncertainties of these 3D space motions, what we found is that it actually appears that M33 is on first infall into the halo of the Andromeda Galaxy. So very different from the picture that was presented. So keep that in mind. We're going to move on to M32, which we now also finally have 3D space motions for. So my collaborator, Mark Fardell, in the HST Chromo collaboration has developed, or rather reduced HST data from this program listed here. So now we can ask a similar question for M32. What are the possible orbital histories now that we know how it's moving relative to its host galaxy M31, and because we also have the information for M33. So we're going to talk about 3-body dynamics. So on the left panel, what I'm showing on the x-axis is look-back time, and on the y-axis is the distance from M31. The purple lines are showing you the resulting orbits for M33, so triangulum, in this 3-body setup. And essentially what that's showing is that regardless of what you assume for M31's mass, you always get a first infall scenario and really little evidence for a recent tidal encounter. M32 is shown in the pink, and you see a couple of interesting things here. It's already very close to Andromeda today. It starts at about 6.5 kiloparsecs in the setup, and it goes through a very recent passage, another passage at about 1 billion years ago, and then depending on what you assume for the mass of Andromeda, you can get diverging orbital histories there. But regardless, there's a couple of close passages around M31. And if we look at this result in a couple of different projections, we can start to see exactly what the dynamics or the 3D interaction looks like. And so here, the horizontal black line is the projected disk plane of M31. And you can see M32's orbit in this far right panel very much crosses through that projected disk plane. So if we look at the system from face on instead, we can actually quantify, does it actually go through the disk in this type of model? And what we find is yes. On the right panel, what you're seeing is that M32 approaches M31 from behind and comes and crashes into it from the front. And so this is one possible orbital solution that we're finding. However, of course, there's a caveat, which is that the distance to M32 is uncertain. So I'm showing this fiducial orbit from the last slide in the black here. And what I'll start populating this figure with is what happens if you change the initial distance, accounting for the distance uncertainty of M32. You start to get a broad diversity of orbital histories. So that means a lot more work is necessary to understand what's the most statistically common orbital history. And we also need to account for things like tidal stripping. We have not yet done that. And finally, if M32 really did collide with the disk of M31, can we find observational signatures of that? And to end, I just want to highlight, okay, this is really interesting. It's 3 galaxies, but the Andromeda Galaxy has a lot going on. You just showed us a picture of all these different satellites and stellar streams. So what does that mean for the larger M31 system? Well, we know by studying our own galaxy and its interaction history that the LMC, a massive satellite, shifts the center of mass of the Milky Way. And that's important to account for when we think about the evolution of all of the other substructures that are less massive also orbiting around the Milky Way. Similarly, I'm finding that M33 causes the same kind of shifting of its host galaxy center of mass. M32 is expected to do the same. So as we start to think about the dynamics of more satellite galaxies orbiting around M31 with many of these upcoming programs, so the green circles are highlighting upcoming HST results and pink is with JWST, we're going to start to be able to ask similar questions of what's going on with these other satellite galaxies. But in order to really capture accurately what's happening between those 3 massive players, we've also got to account for how they're shifting potentially their host galaxy center of mass. So I'll leave you with my summary and I'll questions.
That's right, very good. Couple questions. Go ahead.
Okay, so this is really cool. What happens if you assume the high mass scenario for M32, right? So you assume at your initial starting point of your 3-body simulation, M32 is living in a 10 to 12 K. And so it's this maximal, change in the gravitational potential. How does that impact, for example, interpretation of the M33 first impulse scenario? Does it impact?
Okay, so if I understood correctly, your question is, I'm modeling M32 as a 10 to the 12 halo. What happens? What does that mean in terms of interpreting system? Actually, I'm not modeling it as a 10 to the 12 system. Right. So in this scenario, which I should have mentioned, M32 is in the minor merger setup. So all I've done is taken the stellar mass, abundance matched it to the halo mass that we see today, or that we would expect today. That's the orbital setup I've assumed. However, I have pumped up the mass of M32, at least with just keeping the distance fixed to see, what happens, because the real way to do it is accounting for that tidal stripping properly, right? Which we will do. But when I increase the mass, essentially, as soon as it goes above, right now it's at 6.5 times 10 to the 10. As soon as it hits like 7 times 10 to the 11, it shoots out of M31. So there's like an ejection happening. I don't know how trustworthy that is, just because, again, that's without accounting for all the distance uncertainties, and truly, you should account for the stripping of the mass as it's falling into the halo. But yeah, pumping up the mass of M32 definitely changes things. I have not yet checked what that does for M33, but certainly we can check that, and we will. Thanks.
You said, right?
If there are any indications of these systems interacting in the Milky Way as well now?
So are you asking, are there situations like this, like a 3-body system of this mass ratio?
No, no. So with M31, that would be interacting now. What about the Milky Way in the picture?
Does the Milky Way's gravitational potential affect this setup? Got it. I haven't checked that, but based on other calculations where we've looked at, I've looked at, for example, M33, M31, and then does the Milky Way affect that? The answer was no, because we think that the Milky Way and M31 were much further in the past, and that they're moving closer to each other now. And so, yeah, we don't really think that the Milky Way's potential matters so much, and similarly for the LMC as well.
Okay, one last question. Let's go.
Great talk. You had mentioned that this system shows more recent activity than seen in the Milky Way. I was wondering how many other nearby galaxies are close enough to say what the distribution of high activity versus low activity is in the local universe.
Yeah, that's a good question. So we've definitely observed many stellar streams in other local systems, and definitely upcoming observatories are going to make that data set go even crazier. In order to say what kind of timing is associated to those stellar streams, you have to have some information about the motion of the stars in those structures. And so in the Milky Way and M31, we can obtain those 3D space motions. Outside the local group, it gets a lot harder. because you need to wait for a longer period of time to get a longer baseline to then measure a truly precise, to an extent that you can actually do something with it, set of proper motions. So for now, I would say that we can't really go beyond the local group to really determine the timing. I mean, you can set up an n-body simulation and just make some assumptions, right? Or check a grid of initial estimates. And that's still useful and how we started in these systems, right? But truly, if you want to do it based on the way that they're moving right now, you're sort of limited to the local group. But an exciting thing that Adam showed and what's related to this is that for the M81 system, for example, there's a lot of archival data. And so actually my collaborator in the HST promo collaboration has gotten successfully a program to measure the proper motions of M81 and M82. So though it won't necessarily tell us about the stellar streams or any of those features in that system, it'll at least help us start to understand dynamics at a few megaparsecs away, so if you have the right data set, so this is related to what Jen was saying earlier, right? Like, what do you wish you would have observed 20 years ago or in 20 years in the future? Yeah, so.
Let's thank Lisa for a wonderful talk. A round of applause for all speakers in today. Thank you very much. We're done.
And thank you for all of our wonderful session chairs today. You guys did a great job of keeping folks on time and. Okay, I have a few quick announcements and then we're done for the day. First of all, if you have not submitted your talk for tomorrow, you're giving a talk tomorrow and you have not submitted it, please upload it. It's really easy to do. Please upload it or we'll have to hunt you down tomorrow and we don't want to do that. And it makes Kevin's life harder and we don't want that either. So please make sure you upload your talks. Tomorrow we will start at 10 a.m. with the mentoring and DEI session with Victoria. It's right here. They wrote it somewhere with Victoria. You were emailed material to read a couple weeks ago. If you have not done that, please try to do that before you come tomorrow morning. And we will. Paul said volunteer to put it in the Slack if people didn't see it in their email. Yes. Yes. Okay. I'm volunteering, but he mentioned it. And then
volunteers to do something in Slack, say yes.
Yeah. Paul is not a big Slack user. It's fine, but he's getting better. Okay, and then finally, yes.
Yeah. Thank you. If you have not done the reading, I know, there's other things to do today. If you can check out maybe the first couple of pages, that would be awesome. If not, we'll have it for later. It will be fine. Thank you.
Thank you. That is good clarification. Okay, and then finally, tonight is also Astronomy on Tap with our guest speaker and our chair. So Rohan and Ekta. So it's at the doghouse and we have the information here. If you need it, we can probably also post that in Slack. But so go watch them too, have some fun. And I think that's it. Anything else? I'm looking at Paul and Andy. Okay, have a great evening and we will see everyone back here. Breakfast again will be, I think all the food will be out here, at least that's what Frank said. But breakfast will be here starting at 9. So we will see you all tomorrow, if not later tonight. Okay, everybody, thank you.